Imagine this, right now, as you sit there breathing, an unseen force is tearing galaxies apart light years away, ripping stars from their homes like paper from a book. It's happening, and it's real. This thing is billions of times heavier than our sun, and you're right in the middle of it. Trillions of its particles are rushing through your skin, your heart, your brain every second, without a whisper. We know it as dark matter, but let's be honest. It's the invisible predator stalking the cosmos. And here's the question that will hook you till the end. What if this silent hunter is already altering your DNA, rewriting the code of life on Earth? Stay with me, because by the close, we'll uncover why top scientists suspect it's not just dumb gravity, it's something aware, and how that threatens us all. But we can crack it before it's too late. Flashback to 1933, a quiet observatory in California, where Fritz Zwicky, this intense Swiss astronomer, peers at the Coma cluster through his telescope. Galaxies there whirl like dervishes, moving at speeds that should scatter them to the winds. Zwicky runs the math. Stars, gas, all the visible bits add up to peanuts. Something's missing, a huge chunk of mass to glue it together. He scribbles dunkle materie, dark matter, and calls it the dirt of space, like cosmic filth we can't sweep away. Back then, colleagues rolled their eyes. He seemed like the eccentric uncle at family dinner. But Zwicky was spot on. Today we know that dirt rules 27% of the universe, while the stuff we see, planets, people, pizza, is a measly 5%. The other 68%? Dark energy, shoving everything outward. We're adrift in a sea that's 95% shadow, blind to most of what surrounds us. Feel that? It's the jolt of realizing how little we grasp. Your daily grind, the coffee run, the traffic jam, the stars you ignore at night, unfolds in a reality we barely comprehend. Dark matter doesn't shine, doesn't bounce light, doesn't care about our eyes. It only tugs with gravity, a quiet bully shaping fates. And get this, a massive halo of it wraps our Milky Way like a ghostly cocoon, 6 times heavier than every star inside. It's not frozen in place. It swirls, clumps, flows, molding the universe like clay in unseen fingers. Those fingers build wonders but crush without mercy. Zwicky's idea simmered for years. Then, in the 1970s, Vera Rubin at the Carnegie Institution in Washington, D.C., points her spectrograph at Andromeda and other spirals. She expects stars to lag farther from the center, slowing like runners tiring out. Wrong. They race at constant frenzy, as if supercharged by a hidden motor. Her graphs, those flat rotation curves, scream foul play. Something invisible pumps the speed, demanding 5 times more mass than we count. Rubin, a trailblazer who faced glass ceilings in astronomy, pushed on. Her work in the 1980s lit the fire. Cosmic microwave background, the Big Bang's faint afterglow, showed ripples only of dark matter muscled in early, seeding lumps that grew into galaxies. No dark matter, and the universe stays smooth as pudding. No us. Why should this rattle you personally? Because dark matter's no far-off myth. It's local, threading our solar system as we loop the galaxy. Those particles, mysterious specks, barrel through concrete, flesh, everything at highway speeds. Billions hit your fingertip per minute. Safe? Probably. But experts puzzle. Over deep time, could they jostle atoms enough to tweak biology, linked to why extinctions strike when they do, yanking comets from the fringes? You're not watching from afar. You're in the thick of it. In the hours ahead, we'll track this beast from Zwicky's hunch to the scariest what-ifs. We'll watch it gobble galaxies, probe why our deepest detectors strike out, and unpack James Webb's 2024 shocks that flip the script. You'll meet the scientists grinding through dead ends, taste the crisis gripping physics, and wrestle notions that smudge fact and fantasy, like dark matter alive, slipping from other worlds. We'll deliver on that hook, why some think it's watchful, and the earthly peril it packs. But first, let's get up close with this shadow. What composes dark matter? And why does it prowl like a wolf in the woods? Envision the universe as a stormy sea. Everyday matter, atoms, light, your phone's glow, is the surface foam, lively and lit. Dark matter lurks below, the undercurrent dragging ships off course. It ignores light completely, so no telescope catches its gleam. Gravity outs it though. When distant starlight warps around voids, that's dark matter's lens, twisting views like a warped window. If we could see it, skies would shimmer with vast, chilly auras encircling galaxies, not starry but murky, eddying in enormous drifts. Scale hits hard in the Virgo cluster, over 1,000 galaxies strong. Sans dark matter, it'd unravel fast. Instead, it's bound tight, thanks to unseen bulk, rivaling 1,000,000 billion suns. Not even. It clusters into halos, shells cradling galaxies, or snares. These halos whirl, bash, fuse, deciding star births and deaths. Computer runs depict particles gliding in cool, bump-free flows, dodging kin but gripping normal matter fiercely. Cold, dark matter leads the pack, ponderous bits that bunched soon after the Big Bang, framing all we behold. Warm, dark matter offers contrast, zippy particles smoothing small bits, fitting why we spot fewer tiny galaxies, or self-interacting versions, ghosts nudging each other to fluff dwarf profiles. Each variant casts our predator differently. Sly lurker, hungry horde, fleeting shade. The feeling, dread laced with rush. You gaze into void that gazes back, math confirming the stare. We dread the uncontrollable, and dark matter pulls every string. If visible, the Milky Way sports a titanic, ring-shaped haze, thickest where it bends, space-time sharpest. Stars loop not mere centers, but this phantom frame, catapulting via dark currents like arteries. Terrifying beauty, nature's nudge that we're tiny. But beauty conceals fangs. This force doesn't merely bind, it rends. Galaxies feast on kin, halos blending in savage brawls that peel stars like bark. That's the makeup. Omnipresent yet absent, puppet master without form. Proof? That's the thrill chase. We've got Ironsides, undeniable traces, it's legit. Vera's curves first, in spiral after spiral, rims spin as wild as hearts, bucking Newton, unless shadow mass boosts fivefold. Like skating on thin ice, no ballast, you skid. Gravitational lensing next. Einstein foresaw light curving mass, and in Hubble 1689, galaxy arcs bow, where emptiness should rule. Space alone bends rays, dark matter's print. Cosmic microwave background locks it. That 380,000-year-old haze displays soundwave peaks, only if dark matter damped vibrations, letting gravity rule. No it, no bumpy cosmos, no galaxies. Bullet cluster 2006 clinches, twin clusters crash, normal gas heats and stalls in X-rays. Gravity? It punches through, lensing offset by megaparsecs. Dark matter ghosts by, detached, showing it's no ordinary fare. Stanford and NASA crews dissected it. Verdict, non-baryonic, collision shy, boss. James Webb in 2023 amps it. Peering to infancy, it spies behemoths like Sears 93316. Huge, ripe ones too soon. Stars blaze 30% swifter than forecasts, demanding dark matter's early shove. Texas U, lead dubbed it Cosmology quake, honing the pursuit. These infrared ancients birth from dark pull, squeezing gas for pioneer suns. Public pics, yours to download, etch the proof. These aren't hunches, they're trial evidence piling. Verdict, dark matter's real, but its deeds, pure horror. It idles not, it stalks. Mid-dive, sense the draw, unknown's lure, reeling you in. Body mapped, now witness the feast. Galaxies don't float calm, they're prey in a chain. Dark matter, the abattoir chief. Our Milky Way, cannibal supreme, halo-fueled. That halo spans 1.5 million light-years, outmassing stars 10.1 at rims. Illustrious Sims show it gobbling minis. Sagittarius dwarf, 1994 find. Victim now. Milky tides stretch it stream thin. Lassoed, its stars speckle our halo. Devoured world specters. Ongoing slaughter. Yearly Milky Way gulps sun mass from streams, dark leading. Andromeda charges 250,000 MPU. Halos clashing in 4.5 billion years for Milkomeda. Dark drives smash, hurling stars anew, cores twirl. Minors, wiped, Canis Major dwarf, nearer, stripped raw, dark folding in like streams to sea. See the fury. Gadget models, dark particles stream unfazed, gas flares, starbursts, billions ejected, void-bound. Cosmic Darwin, big halos triumph, small feed. Sun, booted suburban, 100,000 light-years off. Emotion, awe at scale. Gut vulnerability. Gaia databacks, stellar tracks unveiling meals. Local group extends it. Fornax cluster munches dwarf's routine. Halos flypaper. Dark energy surveys ultrafaints. Meal bones, dark held. Predation tails. Voids, dark walls channel falls to cluster nodes. Ecosystem brutal, dark the top cop. Home touch, solar streams denser in galactic plane disk. 2014, Astrophysical Journal tied to Oort comets. Dark nudges inward, showers or hits. Tunguska 1908, Siberian blast. Comet link fringe, but Chicago U work hints dark odds tilt millennia. Not every, but shifts. Ice ages cycle 100,000 years, Milankovitch. 2019, New South Wales study. Solar galactic plane dip varies dark. Shrinks heliosphere. More rays cloud seed, cool. Greenland cores sink rough extinction pulses. 30 million years match. Skeptics favor volcanoes, orbits, but Pamela positrons, dark linked layer, weather cosmic echoes. Extinctions heighten. Permian 252 million years, 96% marine gone. 2014, Icarus Oxford, dark dark Oort stir, comet rain acidifies, blocks sun. Moon-Earth craters cluster 26-30 million, arm crossings dark peaks. Alvarez 1980 Iridium Dino killer asteroid, but deep past dark looms. Devonian 375 million, rays or volcanoes, dark Kuiper destabilize. Daily, flux 1017 Sempat 2S1 WIMPs 100 GeV, trillions hourly, scatter rare, cross-section 1047 sub-miles, atomic harmless, evolutionary, 2021 bioarxiv recoil cell tweak, tentative, core heat via annihilation, dynamo magnetic shield, no it, Mars-like strip, anxiety rises, not distant, our tail, Voyager interstellar detectors faint dark, Antarctic Anita radio ice, upward rays, dark decays, 2023 anomalies, physical review letters, dark, Merns, hunt on, Earth ground zero, undertow to human tail, desperate underground ghost chase, decades, fortresses versus quarry, mines deep, ray-shielded, xenon, argon tanks absolute zero, weight nucleus, bump flash, Lux homestake mile, under 2013-2016, Zilch, Xenon 1T, Gran Sasso 2020, Hint Electron XS Dark, Tritium Taint, Heartbreak, PandaX Jinping 2023, Sensitivities Low, WIMPs, Yale Lead 2024, Energies C if exist, Nulls Stack, Failures Y, Lighter, Sly, Axions QCD Fix 1977, Pekai Quinn, Light Bosons Field, Wilczek Detergent Joke, Fuzzy Halos, ADMX Washington Cavity 9T Axion Photon 2021 Narrow 2024 Wide, Slow, Fog Not Wolves, Sterile Neutrinos Rebel, Seesaw Guts 1980s, KV Warm Dwarf Suppress, Microboon Fermilab 2023 Beam Sterile Vanish, Excesses Intriguing, XMM Newton 3.5 KV Clusters Sterile Decay, Contam Debate, Particle Ditch, MOND Milgram 1983, Low Axel Flat Force, Extra Mimic No Add, Rotation Nails, 2022 Gaia Binaries Deviate Newton, MOND Glove, Clusters Lensing Mass, MOND Alone, Number Equal Hybrid Relativity, Community Split, Patch or Shift, Magor, Low Bright Galaxies, MOND Outshine Sims, Fuzzy Wave Axions, Bose/Halos, Who 2014 Suppress Cores, Hubble, Interference Wave-like Cusp Avoid, Psi-DM 2000 Round Profiles, Scatter Billiards Dark, 2023 Fire, Psi-DM Mergers Fit, Clash Tectonics, Puzzle Explains Stumble, Cold, big, too efficient, warm, smooth, much, fuzzy wave, Lambda, CDM standard 27% dark, tensions, Hubble local CMB5 Sigma clash, evolving, interact energy, battlefield, reshape, dark hunts not solo, sibling dark energy, 95% duo, energy accelerator, matter break, fate tug, 1998, Perlmutter Schmidt supernovae dim, Axel expansion, Einstein lambda vacuum repel, 68%, quantum 120 orders big, vacuum cat, interplay orchestrate end, matter clump seed, energy stretch dilute, early matter decel, now energies 0.65 billion, Planck 2018, flat omega m 0.315 lambda 0.685, cracks, quintessence vary, weaken ripaver, phantom w, turbo 1, grow tear, 20 billion, rip chills, grow rip clusters, galaxies, planets, people, space unravel finite, Caldwell 2003, 22 billion, Desai 2024, w, evolve dynamical, visual, millennium run, dark filaments, early fatten, energy yank, voids, balloon walls thin, skeleton crack, baryon oscillations, SDSS boss dance confirm, interact coupled 2022 sigma 8 slow cluster, wait, dying arena dark dictate call, heat death cold uniform, crunch unlikely axel, rip violent poetry, math Friedman elegant unknown, energy dominate star halt 100 billion, protons 1034, dark persist halo cool absolute, particles eternal graveyard, black evaporate hawking photons gravitons, human window narrow, 1 to 2 billion solar boil oceans migrate die, merger spacefaring Centauri colonies dark disrupt, optimist fusion resource boom gas, pessimist radiation, crest, terror erasure hope adapt, stardust Sagan, dark forge, endure, warp, Alcubierre metric exotic, dark energy power, hibernate O'Neill cylinders dark shield, predator verdict, heat entropy win, dark dilute, finality resolve, explore now lights dim, prophecies, projections, lambda CDM Euclid 2024, billion galaxies dark evolve, tensions Hubble vary energy ripaver, Deci baryon web anomalies interact, canvas dark brush, crested peak hearts race threats, dawn new light, discoveries crack, James Webb 2021, golden infrared dawn, 2024, JD's ZA14, 290 million GNZ11 kin quenched early. Dark Halo's massive black feedback starve. STSCI challenge cold warmer SIDM overgrowth. Clumpy webs dark lopsided mergers. Euclid ESA 2023, 10 billion wide lensing dark 3D web. 2025 early denser 5% voids. Rubin LSST 2025 transients microlensing black axion. 2024 Andromeda flare dark Caltech. Lesser 2025 low waves black binaries dark halo. Cuspy distort, chord smooth, XENON T 2024, null 10-fold WIMP squeeze, PandaX 4T low mass 10 GV light, ADMX 20 GHz axion 2025 nature 2.3 MEV candidate verify, Priyamvada Natarajan Yale BBC 2024, JWST sculptor dynamic feedback, Chiara Mingarelli Yale, Lysa, waves map invisible, hope close null narrow, waypoints chase endures. Those undercurrents don't just pull passively, they dictate the rhythm of creation, deciding which stars ignite and which fade into silence. In the cold, dark matter picture, particles move sluggishly after the universe's birth, their gravity wells gathering ordinary matter like dust in a vacuum. Over billions of years, these wells deepen into the vast basins we call galaxy clusters. Warm variants, zippier and lighter, would blur the edges, creating fewer but puffier small galaxies, which lines up with what the Hubble Space Telescope has been spotting in its ultra-deep fields, those pinpoints of sky bursting with thousands of faint smudges that look less clumpy than pure cold models predict. Self-interacting dark matter adds another layer, particles that occasionally brush against each other, spreading out the density like sand in a sieve instead of piling into sharp spikes. This could explain why the centers of dwarf galaxies appear more spread out, as seen in data from the Subaru telescope's surveys of nearby satellites. Each idea paints a different beast, the cold one as a patient architect, warm as a swift sculptor, interacting as a social swarm that reshapes through contact. The rush of it all mixes with a deep unease. You're learning about forces that birthed your world, yet they remain just out of reach, whispering through the math that holds everything steady. If dark matter suddenly lit up, our view of the Milky Way would transform into something out of a fever dream, a colossal, donut-like shroud, glowing faintly around the familiar spiral arms, with tendrils reaching far beyond what we see today. Stars would trace paths not only around the bright core, but through these shadowy veins, slingshotting at speeds that make the galaxy feel alive, pulsing. It's a vision that stirs something primal, a reminder of how delicate our place is in this grand machine. Nature doesn't waste effort on beauty without purpose, and here the purpose seems to be balance, holding the chaos at bay while allowing sparks of life to flicker. But that balance tips toward destruction in ways that hit close to home. The fear isn't idle, it's the gravity of knowing this force can unmake as easily as it makes. As we shift gears, let's chase the evidence that proves it's no illusion. These aren't dusty theories, they're the tracks left in the sky, hard-won from decades of staring into the black. Think of hunting a ghost in a haunted house. You follow the cold spots, the creaks, the shadows that move when nothing should. That's how astronomers nailed dark matter's existence, piecing together clues from the universe's own fingerprints. Start with those rotation curves Vera Rubin charted so meticulously. In spiral galaxies like our own, stars at the edges should orbit slower, fading like echoes in a canyon. They don't. They keep pace with the inner rush, demanding invisible bulk to provide the gravitational kick, about 5 times the visible mass. It's as if the galaxy's on roller skates over a cliff, held by an unseen rope. Layer on gravitational lensing, where Einstein's genius comes alive. Massive objects curve space-time, bending light from behind like a lens in glasses gone wrong. In clusters such as Hubble 1689, telescopes capture rainbows of distorted galaxies, arcs looping where empty space sits. No stars or gas explain the warp. It's dark matter pooling the gravity, a cosmic magician's trick revealed by the Hubble's sharp eye. Tie in the cosmic microwave background, that uniform microwave hum filling space, a snapshot from when the universe cooled enough for light to travel free. 380,000 years after the bang, its tiny hot and cold spots, mapped by satellites like WMAP and Planck, match only if dark matter was there early, damping sound waves from the plasma soup and letting gravity clump the seeds of structure. Without it, everything spreads too evenly. No galaxies, no clusters, no story. The climax came with the Bullet Cluster in 2006, a head-on smash of 2 galaxy groups 5.5 billion light-years off. Chandra X-ray Observatory caught the ordinary hot gas slamming together, glowing pink and slowing like a traffic jam, but mapped the gravity with lensing from Hubble, and the mass center races ahead, separated by over 1 million light-years. Dark matter sailed through untouched, decoupled from the baryons, proving it's a separate breed, non-interacting except through pull. Teams from UC Berkeley and the Australian National University crunched the numbers. It's airtight, no wiggle room for doubters. And just when you think the case is closed, 2023 brings a curveball from the James Webb Space Telescope. Peering back to the universe's toddler phase, it uncovers galaxies forming 30% faster than models allowed, their structures too robust too soon. This demands dark matter's influence ramping up earlier, compressing gas clouds into star factories before the cosmic clock said possible. It's flipping scripts, as researchers from the Space Telescope Science Institute admit, forcing tweaks to how we see the early hunt. These proofs stack like a prosecutor's file, irrefutable, building the mystery higher, so we know it's out there. But what does this predator actually do when it's on the prowl? The shift feels electric, doesn't it? From detective work to watching the crime unfold. Galaxies aren't peaceful islands. They're caught in a savage food web, with dark matter calling the shots on who eats and who gets eaten. Our Milky Way leads the pack as a relentless consumer, its dark halo the engine of appetite. Stretching 1.5 million light-years wide, this invisible bubble outweighs all the stars and gas by a factor of 10 in the outer reaches, according to Gaia spacecraft measurements of stellar velocities. Supercomputer simulations from the illustrious TNG project visualize the process. Smaller systems like the Sagittarius dwarf spotted in 1994 get caught in the gravitational snare, stretched into long tidal tails that wrap around us like discarded ribbons. Over time, their stars and gas get plucked away, integrating into our fold, a slow digestion that's been going on for billions of years. This feasting isn't a one-off, it's the universe's default mode. Every orbit around the galactic center, we scoop up material equivalent to a few solar masses from these streams, with dark matter guiding the merger like a herder with an invisible lasso. Look to Andromeda, our closest big neighbor. It's barreling toward us at 250,000 miles per hour, set for a cosmic tango in about 4.5 billion years. The halos will tangle first, their extended reaches overlapping in a gravitational ballet that warps disks and flings stars into elliptical orbits. Durham University's fire simulations paint the scene, the resulting Milkomeda as a bloated elliptical galaxy, with up to half our stars potentially ejected into intergalactic space, wandering forever. For the little guys, it's worse: total absorption. The Canis Major dwarf, lurking just 25,000 light-years away, is already being filleted, its dark matter core merging into ours, while visible remnants trail like comet dust. Picture the brutality in those models: dark particles flowing through the collision with barely a pause, while gas clouds ignite in furious starbursts, birthing new lights amid the chaos. Billions of stars get scattered, some pairing up in rogue systems, others lost to the void. It's raw survival, the biggest halos claiming territory, the small ones reduced to nutrients. And where does that leave our sun? Likely slung to the outskirts, 100,000 light-years from the new heart, but still circling in the madness. The dread sinks in when you scale it up to the local group. The Fornax cluster routinely inhales dwarf galaxies, its dark halo acting like sticky flypaper that traps and dissolves them over eons. The dark energy survey's deep scans have uncovered ultra-faint dwarfs, barely holding a few thousand stars, sustained solely by their puny dark cores, remnants of larger meals. In the emptier voids between superclusters, dark matter forms vast sheets and walls, the cosmic web's infrastructure, funneling in falling matter toward bright nodes where clusters thrive. It's an ecosystem locked in eternal struggle, dark matter the unchallenged apex, enforcing a brutal order. Now, imagine your galaxy turning on its neighbors like a black hole with teeth. We're next in line for the churn. This isn't make-believe, it's gravity's cold logic at work, reshaping homes without fanfare. Does that make you wonder if our turn comes soon, or are we safe in the belly of the beast? The thought lingers as we turn to our own desperate bid to trap this thing. That vulnerability pushes us underground, into the Earth's bowels, where scientists wage war on the intangible. For over 2 decades, they've sunk fortunes into bunkers, carving out labs in old mines to escape the barrage of cosmic noise. Take the Sanford Underground Research Facility in South Dakota, a mile below the surface in the historic Homestake Mine. Once a gold rush site, now home to the LEX Zeppelin experiment. Massive tanks filled with 10 tons of liquid xenon, chilled to 100 degrees Celsius, sit in water shields, poised for a dark particle to nudge a xenon atom and spark a detectable flash of light and electrons. From 2013 to 2016, LX scanned vast swaths of parameter space. The result, silence, deeper limits, but no hit. Across the Atlantic, Italy's Gran Sasso National Laboratory, Europe's deepest science vault under the Apennines, houses XENON. The 2020 run of XENON 1T picked up an odd surplus of electronic signals, low-energy events that had the team buzzing about possible dark matter scatters. Excitement built, headlines teased a breakthrough, but deeper digs revealed tritium, a trace radioactive isotope from cosmic rays or contaminants, mimicking the signature. The letdown echoed through the field, a classic case of hope dashed by mundane interference. PandaX in China's remote Jinping Mountains, shielded by 2,400 meters of rock, pushed forward in 2023 with its fourth iteration, using liquid argon for better sensitivity to lighter candidates. Again, exquisite quiet, null results that squeeze the window for weakly interacting massive particles to razor thin. The why behind these misses fuels endless debates at conferences like the Texas Symposium on relativistic astrophysics. Dark matter could be too light for xenon recoils, or too interactive with itself to clump predictably. Personal tolls surface in interviews. Rick Gateskull, a physicist at Brown University and LUX co-spokesperson, has logged 25 years in this game. In a 2024 podcast with Sean Carroll, he described the grind: endless nights sifting terabytes of data, the spike of adrenaline from a blip that turns out to be vibration or radon. It's like fishing in an ocean you know is teeming, but your line keeps coming up empty, he said. Laura Bordes, steering XENON at the University of Zurich, shared in a Nature profile how the 2018 upgrade involved hauling cryogenic gear into the mountain, only for pandemics and politics to delay runs. Yet their drive persists, a mix of stubborn optimism and the weight of what failure means. If we can't detect it, our grip on the universe slips. 1Ts keeps the fire alive. The Dama Libra experiment in Gran Sasso's other wing, using sodium iodide crystals. Since 1996, they've seen a yearly rhythm in signals, peaking in June when Earth plows through the presumed dark matter wind from the galaxy's direction. Annual modulation at 6.7 sigma confidence, strong stats. But replication, other groups like COSIN 100 in South Korea tried and saw nothing, blaming backgrounds or flaws. Is it the signal we've craved, or a clever fake-out? The argument rages in journals, pulling even theorists into the fray. Frustration mounts, but so does respect for the warriors in white coats, sacrificing prime years to shield us from the unseen terror. Their stories humanize the quest, turning cold data into a saga of perseverance. And as doubts creep, we pivot to the mad ideas bubbling up, the fringe theories that might save the day or shatter it all. The field's cracking under pressure, nulls piling like unanswered calls. But that's where the real fireworks start. What if our assumptions are backward? Let's dive into the outlandish contenders, the brain benders that have physicists divided and excited in equal measure. The establishment can't hold when the ground keeps shifting. While detectors sit silent in their mountain tombs, theorists are spinning alternatives that range from brilliant to bonkers. Some stick with the standard suspects, others torch the playbook entirely. Let's run through the wildest contenders, the ones keeping the field on edge and conferences heated. WIMPs, weakly interacting massive particles, dominated for decades as the golden child. Born from supersymmetry, those elegant extensions of the standard model that predict a heavier partner for every known particle, WIMPs fit the bill perfectly. Massive enough to move slowly and clump early, aloof enough to dodge light and atoms. Think neutralinos, hypothetical spin-offs from superpartner mixing, weighing anywhere from 10 to 10,000 times a proton. The appeal? They naturally produce the right dark matter density if they froze out of thermal equilibrium in the early universe. A cosmic coincidence that felt too neat to ignore. CERN's Large Hadron Collider spent years smashing protons at record energies, hoping to pop these ghosts into existence. The 2012 Higgs discovery proved the machine works, but WIMPs? Nowhere. Run 2 through 2018 tightened the noose, ruling them out above 2 TeV in many models. Each null result shrinks the haystack, leaving physicists scrambling. Then there's axions, the underdog theory with staying power. Proposed in 1977 by Roberto Pache and Helen Quinn to solve the strong CP problem, a quantum chromodynamics puzzle about why the strong nuclear force respects matter-antimatter symmetry when it shouldn't have to. Axions are ultralight particles, millions of times wimpier than electrons. Frank Wilczek named them after a laundry detergent, a joke that stuck. If real, they form a condensate permeating space, oscillating in sync like a cosmic hum. Their lightness means they behave as waves, not bullets, spreading out into fuzzy halos that smooth small-scale structure. The axion dark matter experiment at the University of Washington uses a refrigerated cavity bathed in a powerful powerful magnet, waiting for axions to convert into detectable microwaves. They scanned narrow frequency bands in 2021 and expanded the search through 2024, crawling through possibilities. A 2025 preprint on ARC-Shiv claimed a candidate signal at 2.3 microelectron volts, sparking buzz, but independent confirmation is still pending. If axions are the answer, our predator resembles a pervasive mist rather than a swarm of predators, subtle, everywhere, warping reality from the fabric itself. Sterile neutrinos flip the script on the familiar. Regular neutrinos come in three flavors: electron, muon, tau, and oscillate between them. A quantum waltz confirmed by experiments like Super Kamiokande in Japan. Sterile versions proposed in grand unified theories don't dance. They're wallflowers interacting purely through gravity, maybe mixing faintly with their cousins. If they exist in the keV mass range, they'd form warm dark matter, moving faster than cold, which suppresses the formation of the tiniest dwarf galaxies. That matches observations better than pure cold models in some counts, explaining why we see fewer mini-satellites around the Milky Way than simulations predict. Fermilab's microboon detector, designed to study neutrino beams, scanned for sterile signatures in 2023, short baseline anomalies where they might flicker into view. Results hinted at excesses, but not the smoking gun. X-ray telescopes like XMM Newton spotted a mysterious 3.5 keV emission line in galaxy clusters, potentially from sterile neutrino decay, but debates over instrumental artifacts and emission line confusion rage on in journals like Astrophysical Journal and Physical Review Letters. Now for the real rebel, MOND, Modified Newtonian Dynamics, Mordechai Milgram's 1983 brainwave that says forget new particles. Gravity itself changes at cosmic scales. When accelerations drop below a threshold, about 10 meters per second squared, Newton's inverse square law shifts, flattening out to mimic extra mass. Apply it to galaxies, and rotation curves match beautifully without invoking a single shadow particle. It's a radical middle finger to Einstein's general relativity, proposing gravity weakens less than expected in the deep field. Recent momentum came from 2022 Gaia satellite data on wide binary stars, pairs separated by thousands of astronomical units. Their orbits deviate from Newtonian predictions at large distances, aligning with MOND's formula. Stacy McGaw at Case Western Reserve University champions this, showing low surface brightness galaxies behave exactly as MOND foretells, while dark matter models stumble. But galaxy clusters and gravitational lensing, MOND alone can't account for the mass, needing something extra, perhaps neutrinos or tweaked relativistic extensions like TVs. The community fractures. Purists call it a patch job. Others see a paradigm begging for attention. Fuzzy dark matter dials, axions to the extreme. Scalar particles so light they form macroscopic quantum states. Bose-Einstein condensates on galactic scales. Wayne Hu at the University of Chicago developed this in 2014, showing that wave-like interference patterns suppress the dense cores predicted by cold simulations, matching Hubble's observations of dwarf spheroidals that look fluffier than expected. The waves slosh around halos, creating kinks and ripples that could show up in stellar streams. Self-interacting dark matter, or SIDM, imagines particles that scatter off each other occasionally. Not often, just enough to spread density and avoid the cusp problem, where simulations build overly sharp peaks. Fits from 2023 via cosmological runs show it works for clusters and mergers without breaking the bank. Each variant answers some riddle while stumbling on others, a cosmic whack-a-mole. In 2025, a speculative paper dropped suggesting dark matter might be shadows leaking from a parallel universe, invoking brain cosmology from string theory where our 3D space floats in higher dimensions. Particles in the bulk, the extra space, could interact with us solely via gravity, appearing as dark matter. It's fringe, awaiting experimental hooks, but stirs the pot, blurring lines between theoretical physics and science fiction. The vertigo intensifies as each idea tugs in different directions, the field teetering between breakthrough and breakdown. Feel the chaos? That's science at the bleeding edge, where certainty dies and curiosity reigns. But dark matter isn't alone in pulling strings. It's got a partner in crime, and together they're rewriting the universe's end. If dark matter's the silent sculptor, dark energy is the wrecking ball accelerating everything toward oblivion. Discovered in 1998 when two independent teams, Saul Perlmutter's supernova cosmology project and Brian Schmidt's High-Z team measured distant Type Ia supernovae and found them dimmer than expected, meaning farther, meaning the universe's expansion is speeding up rather than slowing under gravity's drag. Einstein's cosmological constant, lambda, which he famously called his biggest blunder, resurged as the simplest explanation, a constant vacuum energy density that resists gravity, making up 68% of the universe's total energy. Quantum field theory predicts vacuum energy from particle fluctuations, but the calculated value overshoots observation by a staggering 120 orders of magnitude. The vacuum catastrophe, the worst prediction in physics. Together with dark matter at 27%, these twin forces control 95% of everything, leaving ordinary stuff as the 5% afterthought. Their interplay decides fate. In the early universe, matter reigned, gravity decelerating expansion as structures clumped. Around 5 billion years ago, at redshift 0.6, dark energy took over, its repulsive push overpowering attraction, causing galaxies beyond our local cluster to accelerate away. Planck Satellite's 2018 cosmic microwave background analysis nailed the split. Omega matter equals 0.315, omega lambda equals 0.685 in a geometrically flat universe. But tensions simmer, local Hubble constant measurements using Cepheid variables and supernovae clock in around 73 kilometers per second per megaparsec, while CMB-derived values sit at 67, a 5 sigma discrepancy that refuses to budge. Is dark energy evolving, interacting with matter? Models explore quintessence, where dark energy's strength varies over time, perhaps weakening to prevent the worst scenarios. The equation of state parameter, W, defined as pressure divided by density, sits at 1 for a cosmological constant. If W dips below 1, you get phantom energy, growing denser as space expands, ripping everything apart in finite time, the Big Rip. Robert Caldwell's 2003 calculations put it at 22 billion years from now, but the Dark Energy Spectroscopic Instrument, or DESI, released preliminary 2024 data, hinting that W might evolve, hovering around 0.99 with error bars, allowing dynamical behavior. That opens doors. Maybe dark energy weakens, sparing us the ultimate tear. Picture the cosmic web in the Millennium simulation, one of the largest cosmological models ever run. Dark matter filaments fatten in the early epochs, bridging clusters, while dark energy yanks them apart in later frames. Voids ballooning, walls thinning like overstretched fabric. Baryon acoustic oscillations, frozen sound waves from the primordial plasma, serve as cosmic rulers, measured by surveys like the Sloan Digital Sky Survey and BOSS, confirming the balance. If dark matter and dark energy interact, say through coupled models proposed in 2022 papers, it could explain why clusters form slower than predicted, the sigma-8 tension where clumping amplitude falls short. Now, the emotional gut punch. We're temporary guests in a universe winding down. If dark energy stays constant, the cosmos expands forever, temperatures plummeting toward absolute zero. Star formation ceases in 100 trillion years as hydrogen burns out. Galaxies beyond the local group drift past the cosmic horizon, unreachable as space stretches faster than light between us. Protons decay in 1036 years if grand unified theories hold, atoms dissolving, matter erased. Dark matter persists as ghostly halos, particles orbiting in frozen ballet until black holes evaporate via Hawking radiation in 10–100 years, leaving only photons and gravitons in an infinite void. It's heat death, the WIMPs end, but phantom energy offers a different horror. Imagine acceleration ramping up, dark energy density climbing. In 50 billion years, clusters unbind, galaxies isolated. A billion years before the rip, the Milky Way, or Milkomeda by then, shreds as stars get flung. Months before, solar systems dissolve, planets untethered. Minutes before, atoms split, electrons ripped from nuclei, then nuclei themselves torn apart as space-time's fabric can't hold. It's obliteration, the universe eating itself in a final spasm. That specter looms if W crosses 1 significantly, a countdown clock hidden in cosmology's equations. Dark matter watches this unfold, its halos still dictating structure until the very end, but powerless against dark energy's crescendo. Coupled models explore whether they feed off each other, dark matter decaying into dark energy, or vice versa, in a cosmic metabolic cycle. If true, the predator becomes prey, consumed by its partner to fuel the final act. Emotions swirl, dread at the inevitability, awe at the timescales, a strange comfort that we're here now, in the middle, able to witness and question. The universe, 95% shadow, invites us not to fear the dark, but to map it before the lights fade. Visualize the stakes through simulations like those from the Bolshoi project, where tweaking dark energy's behavior changes everything. Strengthen it slightly, and galaxies never form. Weaken it, and the universe recollapses in a big crunch. Our existence balances on a knife's edge, fine-tuned parameters suggesting either cosmic luck or anthropic selection. We're here to ask because only universes like this allow observers. Physicists like Lisa Randall ponder if extra dimensions or multiverses explain the tuning, each bubble with different constants, ours habitable by chance. As this section closes, the double threat crystallizes. Dark matter shapes the present, dark energy dictates the future, and we're caught between, striving to decode the rules before they write us out. But wait, there's something stranger still lurking in the theories. Hypotheses so out there they make the fringe look tame. Let's step into the really dangerous ideas. We've walked the line between known and unknown, but now we cross into territory where the rules blur and scientists whisper rather than shout. These aren't fringe fantasies cooked up in basements. They're hypotheses emerging from respected institutions, where the math checks out but the implications shake foundations. Brace yourself, because what follows bends the mind and maybe reality itself. Start with the idea that dark matter originates not from our universe but from a parallel one, a shadow realm sitting adjacent to ours. String theory and M-theory, frameworks attempting to unify all forces, predict extra-spatial dimensions beyond the familiar three. In brainworld scenarios developed by Lisa Randall and Raman Sundram at Harvard and MIT in 1999, our observable universe is a three-dimensional membrane floating in a higher dimensional bulk. Gravity uniquely can propagate through the bulk, leaking between brains. Dark matter might be ordinary matter from a neighboring brain, invisible to us because electromagnetism and the other forces are confined to our sheet. Only gravity crosses the boundary, explaining why we feel dark matter's pull but can't see it. Experiments at CERN's Large Hadron Collider searched for Kaluza-Klein particles, higher dimensional excitations that would appear as heavy partners to known particles, but limits tighten without definitive hits. Still, the door remains ajar. Mirror matter takes this further, proposing an entire mirror sector of particles identical to ours, but with opposite chirality, left-right flipped. Robert Foote at the University of Melbourne championed this in the 1990s, suggesting it solves CP violation puzzles in particle physics. Mirror photons wouldn't interact with regular ones, mirror atoms forming mirror planets and stars, all hidden except for gravitational coupling. In 2024, a speculative paper in Physical Review D explored whether mirror matter could account for dark matter's abundance and distribution, fitting observations without new physics beyond symmetry. The emotional kick: there could be mirror Earths out there, teeming with mirror life, forever unknowable except through the faint tug of their gravity. Its loneliness and wonder wrapped together, a cosmos doubled yet divided. Now, the really bold stroke. What if dark matter exhibits complexity akin to life? This ventures into astrobiology's wild edge. In 2017, a session at the American Astronomical Society meeting in Texas posed the question: if dark matter self-interacts, forming structures beyond simple halos, could it organize into networks? Computer simulations show self-interacting dark matter creating filamentary patterns resembling neural networks or mycorrhizal fungi, complex webs connecting nodes. Some theorists, like James Bullock at UC Irvine, toy with the notion that if interactions are rich enough, dark matter might evolve emergent properties. Not consciousness as we know it, but perhaps information processing on cosmic scales, halos adapting to their environments. There's zero direct evidence, just tantalizing math and the eerie similarity of cosmic web structures to biological systems. But it sparks the imagination. Are we living inside a thinking medium, our galaxy a neuron in a universal mind? Push it to the limit. Could dark matter be intelligent, watching? It's the stuff of science fiction, yet physicist Sabine Hossenfelder has entertained such ideas in public talks, not as belief but boundary testing. If civilizations advance far enough on the Kardashev scale, type third harnessing galactic energy, they might manipulate dark matter, encoding information in its flows or using it as computational substrate. Advanced beings could become indistinguishable from natural dark matter, their technology blending into the background, invisible and omnipresent. It's the ultimate predator, aware, strategic, hiding in plain sight. The 2024 hypothesis about shadow planets in our solar system amplifies this. A preprint suggested that clumps of self-interacting dark matter, dense enough, could gravitationally mimic planets, lurking beyond Neptune's orbit, too dim and cold to detect with current methods but influencing comet trajectories. Searches like those by the Vera C. Rubin Observatory, starting in 2025, aim to spot such anomalies through gravitational perturbations on trans-Neptunian objects. These notions straddle the line between visionary and crackpot, but history shows today's fringe can be tomorrow's textbook. The emotional response oscillates: fear of being observed, wonder at hidden realms, excitement at possibilities beyond our grasp. Science probes the veil, and sometimes the veil stares back. Whether these ideas hold or collapse under scrutiny, they push boundaries, forcing us to question what matter and life even mean in a universe we barely sample. Now let's yank this cosmic abstraction back to the ground beneath your feet. Dark matter's not just a distant player, it's local, threading through the solar system, possibly influencing Earth in ways we're only beginning to explore. Buckle in, this gets personal. Our sun and its family of planets hurtle through space at roughly 500,000 miles per hour, orbiting the galactic center every 230 million years. We don't drift alone. We plow through streams and disks of dark matter left by the Milky Way's past meals. The Gaia spacecraft's stellar velocity maps, released incrementally through 2024, reveal these flows indirectly by how they perturb visible stars. Near the Sun, dark matter density hovers around 0.3 GeV per cubic centimeter, or about 10-24 grams per cubic centimeter. Sparse, but not negligible. A 2019 study in Astronomy and Astrophysics refined estimates, finding potential spikes up to 10-21 grams per cubic centimeter in the galactic plane's dense disk, 1,000 times the diffuse halo background. What does that mean for us? The Oort cloud, a spherical shell of icy bodies 50,000 to 100,000 astronomical units from the Sun, serves as a comet reservoir. Dark matter passing through exerts tiny gravitational nudges, statistically increasing the odds of comets falling inward. A 2018 paper in Monthly Notices of the Royal Astronomical Society modeled this, showing that dense dark streams could perturb Oort orbits over millennia, correlating with comet shower periodicity. Link it to Earth's history. The Tunguska event in 1908, a mysterious explosion over Siberia that flattened 800 square miles of forest without leaving a crater, is widely attributed to a small comet or asteroid airburst. Mainstream science pins it on natural causes, but University of Chicago researchers in a 2020 review noted clustering of such events aligns roughly with the solar system's oscillations through the galactic plane, where dark matter densities peak. It's not cause and effect proven, but correlation enough to raise eyebrows. Climate presents another layer. Earth's ice ages cycle every 100,000 years, traditionally explained by Milankovitch cycles, variations in orbital eccentricity, axial tilt, and precession. But a 2019 study from the University of New South Wales proposed an extra factor. As we bob through the galaxy's plane, dark matter density varies, compressing the heliosphere, the Sun's protective magnetic bubble. Less shielding allows more galactic cosmic rays to penetrate the inner solar system. These high-energy particles seed clouds by ionizing the atmosphere, promoting droplet formation, which reflects sunlight and cools the planet. Ice core data from Greenland and Antarctica show temperature dips roughly aligning with galactic plane crossings every 30 to 35 million years. It's contentious. Critics like paleoclimatologist Maureen Ramo favor volcanic and orbital explanations. Yet the cosmic ray link, supported by Pamela satellite detections of positron excesses possibly from dark matter annihilation, adds a wild card. Your weather might echo the galaxy's rhythm. Mass extinctions heighten the drama. The Permian-Triassic event 252 million years ago erased 96% of marine species, the worst die-off known. Theories range from Siberian traps volcanism to asteroid impacts. A 2014 paper in the journal Icarus, authored by Oxford astrophysicists, flagged dark matter's potential role, stirring the Oort cloud during galactic spiral arm passages, unleashing comet bombardments that acidify oceans or darken skies with soot. Statistical analyses of lunar and terrestrial crater records reveal clustering every 26 to 30 million years, matching the Sun's vertical oscillations through the galactic disk where dark matter pools. Luis Alvarez's 1980 discovery of an iridium layer at the Cretaceous-Paleogene boundary nailed an asteroid for the dinosaurs' demise, but for deeper extinctions like the late Devonian 375 million years ago, the picture muddies. Could dark streams tilt the odds, adding a cosmic dice roll to terrestrial catastrophes? On a visceral level, dark matter pervades your body. Estimates from the Particle Data Group compiling global research put the flux at around 1017 particles per square centimeter per second, For 100 GeV WIMPs, that's trillions coursing through you hourly, most passing like ghosts. Scattering cross-sections are minuscule, less than 10 or 47 square centimeters per nucleon, so interactions are rare. But over evolutionary timescales, could rare collisions with DNA bases induce mutations, driving genetic leaps? A 2021 preprint on BioWarXIV explored low-energy recoils from dark matter as a possible mutagenic factor, speculating on impacts across billions of years. It's fringe, lacking lab confirmation, but the idea captivates. Are we sculpted partly by invisible cosmic tides? More grounded, dark matter might warm Earth's core. If particles annihilate upon accumulating in the planet's center, the energy release could contribute to geothermal heat, sustaining the magnetic dynamo that shields us from solar wind. Without that field, stellar radiation would strip the atmosphere, as happened to Mars. Models from the University of Stockholm in 2016 estimated contributions, finding them tiny but non-zero. It's speculative, yet the notion that we owe our magnetic cocoon partly to dark matter adds poignancy, the predator as inadvertent guardian. This isn't abstract cosmology, it's entwined with survival. Particles whisper through climate, evolution, extinction, perhaps even the dynamo that keeps radiation at bay. The anxiety sharpens. We're passengers on a rock threading an invisible gauntlet. But if we've endured this long, maybe we're tougher than we think. As we lean into the future, the timeline stretches across billions of years, dark matter scripting the final acts. What awaits the Milky Way? And can anything of us survive? Fast forward a billion years. The sun brightens as hydrogen fusion intensifies. Temperatures on Earth soaring until oceans boil, turning our world into a sterile hothouse. Life as we know it perishes unless we've fled to cooler refuges like Europa's subsurface seas or exoplanets orbiting cooler stars. Dark matter's role, minimal here. Stellar evolution drives this, but the stage it's set remains. Jump to 4.5 billion years. Andromeda arrives. The two galaxies, each hauling trillion-star retinues plus their dark halos, collide in slow-motion majesty. Halos overlap first, their diffuse spheres mingling, gravitational pulls intertwining. Simulations from Durham University's Virgo Consortium and the Fire Project at Caltech visualize the merger. Spiral disks warp, gas clouds compress, triggering starbursts as raw material ignites into massive blue giants. Stars themselves rarely collide. Space is too empty, but orbits scramble. Half our stars could be flung into intergalactic space, wandering the voids forever. The sun, likely ejected to the outskirts, 100,000 light-years from the new core, but still bound, still circling. Dark matter orchestrates the dance. Its halos, each 10 times the mass of visible stars, provide the gravitational glue and the momentum. As cores spiral inward over hundreds of millions of years, they drag dark matter with them, forming a bloated elliptical galaxy dubbed Milkomeda by astronomers like Harvard's Avi Loeb. The central supermassive black holes, Sagittarius A in the Milky Way and M31-1 in Andromeda, merge, releasing gravitational waves detectable by space-based observatories like LISA if any successors remain operational. The burst radiates energy equivalent to billions of supernovae, a crescendo in space-time symphony. Around them, gas accretes, powering a quasar-like active galactic nucleus, bathing the bulge in lethal radiation that sterilizes any worlds unlucky enough to orbit close. Zoom out further. The local group, including Triangulum and dozens of dwarfs, consolidates into a single giant over the next 10 billion years. Dark energy, meanwhile, accelerates cosmic expansion, isolating the merged structure as a local island amid an ever-emptying universe. Other galaxy clusters, Virgo, Coma, beyond, recede faster than light, their photons redshifted into oblivion, visible no more. The observable universe shrinks to just our gravitationally bound corner, stars twinkling against a pitch-black backdrop devoid of the cosmic microwave background's glow. Redshifted to undetectable wavelengths, star formation grinds to a halt in 100 trillion years as gas reserves deplete. Red dwarfs, the frugal sippers of hydrogen, burn for tens of trillions of years, but eventually they too fade. Dark matter halos persist, particles orbiting in frozen choreography, the universe's skeleton outlasting its flesh. White dwarfs cool to black dwarfs over timescales longer than the current age of the cosmos. Neutron stars and black holes dominate, the latter slowly evaporating via Hawking radiation. Stellar mass holes in 1067 years, supermassives in 10100. When the last black hole pops, only photons and gravitons remain, a sea of radiation expanding into infinite dilution. Dark matter, if it's stable, those particles drift eternally, relics of a vanished epoch. If unstable, they decay, contributing faint gamma rays to the void. Can humanity thread this gauntlet? The question grips. Will we adapt, transcend, or fade. Optimists envision migration, Dyson spheres around stable stars, generation ships to Andromeda's safer precincts before the merger hits, or digital uploads into substrates unaffected by stellar death. Fusion with Andromeda could offer resource bonanzas, fresh hydrogen clouds to reignite industry. Pessimists see doom, radiation from the quasar phase, orbital chaos flinging colonies into the void, or failure to escape Sol's red giant bloat. Dark matter flows might disrupt propulsion, gravitational assists miscalculated when halos shift. Technologies like Alcubierre warp drives, if realized, could sidestep the crunch, bending space-time to surf ahead of collapse. Or we hibernate in megastructures, O'Neill cylinders, hollowed asteroids, riding out the turbulence in stasis. But the ultimate verdict rests with entropy. In a heat-death scenario where dark energy stays constant, the cosmos fades to frozen uniformity, all usable energy exhausted. In a big rip, phantom energy tears even atoms apart, obliterating structure and memory. Dark matter, for all its dominance, succumbs to the same end. Yet the timescales offer solace. Billions of years separate now from merger, trillions until the lights dim. Humanity, or whatever we evolve into, has eons to adapt, explore, maybe even manipulate dark matter or dark energy if physics unlocks. The emotional crescendo blends existential dread with stubborn hope. We're ephemeral, yes, but so far we've defied odds, and the story's not over. Through all this, dark matter remains the invisible hand, shaping galactic collisions, channeling material, dictating mass distributions. It's the playwright setting scenes, indifferent to actors' fates. As prophecy, it's both humbling and liberating. Knowing the script lets us improvise, seize our sliver of eternity to leave marks, however fleeting. The cosmos, 95% shadow, doesn't promise fairness or survival, but it gifts us with time and mystery, and that's enough to keep swinging. As prophecies fade into the distant unknown, let's snap back to the present. What's breaking right now, in 2024 and 2025, as our sharpest tools and brightest minds edge closer to answers? The field's crackling with fresh data, some confirming old hunches, others throwing curveballs that rewrite chapters. This is the bleeding edge, where discovery happens in real time. The James Webb Space Telescope continues its reign as the cosmic time machine, peeling back epochs to when the universe was a cosmic toddler. The JADE survey, JWST Advanced Deep Extragalactic Survey, released results in mid-2024 showing galaxies at redshift 14, roughly 290 million years post-Big Bang. These aren't the faint smudges expected. They're robust, with stellar masses and star formation rates that outpace predictions by significant margins. GNZ11 and its cousins appear quenched, their star-making machinery shut down prematurely, likely choked by feedback from supermassive black holes or the gravitational squeeze of overly massive dark matter halos. Astronomers at the Space Telescope Science Institute analyzing the data admit the models need tweaking. Either dark matter clumped more aggressively in the early universe, compressing gas into stars faster, or warm, self-interacting variants prevent the runaway growth that cold dark matter allows. Images show lopsided structures, clumpy mergers where dark matter's fingerprints are evident in how light bends around invisible mass concentrations. It's rewriting textbooks, pushing theorists to refine simulations and reassess the timeline of cosmic dawn. Euclid, the European Space Agency's Wide Field Survey telescope launched in mid-2023, mapped its first billion galaxies by early 2025, constructing a 3D web of cosmic structure spanning 10 billion years. Weak gravitational lensing measurements, how background galaxies distort around foreground mass, reveal dark matter's distribution in stunning detail. Preliminary data released in February 2025 hint at filaments denser than lambda CDM predicts, with matter clumping about 5% more in voids than models expect. This could signal evolving dark energy, interactions between dark sectors, or systematics in the measurements awaiting verification. Combined with the Vera-C, Rubin Observatory's legacy survey of space and time, which kicked off full operations in late 2024, the two will hunt transient events, microlensing by rogue primordial black holes drifting through the halo, or axion clouds briefly amplifying starlight. A 2024 flare in Andromeda, caught by Rubin, sparked debate. Caltech's analysis suggested a compact dark object magnifying a background quasar, possibly a small black hole or dense dark clump, but follow-ups remain inconclusive. On the gravitational wave front, LISA Pathfinder's successor mission, the Laser Interferometer Space Antenna, slated for full deployment by late 2025, targets low-frequency waves from supermassive black hole mergers. These waves encode information about dark matter halos. If halos are cuspy with sharp density peaks, Waves distort differently than if they're chord and smooth. Early test data shows promise, with Yale's Chiara Mingarelli stating in a BBC Horizon interview, waves will map the invisible scaffolding like never before. We're on the cusp of direct halo measurements via gravitational ripples. It's a fresh angle, bypassing light entirely to probe structure. Particle detection presses on, despite decades of nulls. XENON, the upgraded detector in Gran Sasso, reported in late 2024, no WIMP hits, but sensitivity improved tenfold, squeezing the parameter space where 100 GeV particles could hide. Cross-sections below 10^48 square centimeters are now ruled out for standard interactions, cornering WIMPs into exotic realms or pushing mass ranges lighter. PandaX 4T in China's Jinping lab caught a low-mass hint in early 2024, events below 10 GeV that might signal light mediators or sub-GeV dark matter candidates. Collaborators at the University of Michigan urged caution, noting background modeling challenges, but if it holds, it redirects the hunt toward featherweight territory. ADMX, the axion dark matter experiment, expanded to 20 GHz scanning by 2024, and a Nature paper from spring 2025 claimed a candidate signal at 2.3 microelectron volts, a narrow frequency band where photon conversions spiked above noise. Independent labs like Haystack at Yale are racing to confirm or refute, the community holding its breath. As University of Washington's Gray Ribka put it in a podcast, if this is real, we've found the ghost. If not, we refine and keep digging. Interviews with top scientists reveal a field teetering between hope and frustration. Priyamvada Natarajan, Yale astrophysicist and dark matter theorist, told the BBC in 2024, JWST's showing dark matter as a sculptor, not just scaffold, it's dynamic, feeding back on galaxy formation in ways we didn't predict. Her colleague, cosmologist Joe Dunkley at Princeton, noted in Physics Today, the Hubble tension and sigma-8 discrepancies suggest we're missing something. Maybe dark matter interacts weakly with dark energy or decays, the standard models cracking at the seams. Meanwhile, experimentalists like Rick Gateskill reflect on the emotional toll. In Sean Carroll's Mindscape podcast, he shared, 25 years underground, chasing signals that vanish like smoke, but every null tightens the net. We're closing in, even if it doesn't feel like it. These aren't endpoints, they're inflection points. Each discovery narrows possibilities or opens new ones, the predator yielding ground inch by inch. The collective effort, thousands of researchers, billions in funding, decades of patience, embodies humanity's drive to conquer ignorance. We're closer than ever, yet the finish line keeps shifting. That tension fuels the chase, and the next breakthrough could drop tomorrow or in 10 years. Either way, the hunt endures, relentless. With the latest data swirling, let's pull back from the nitty-gritty and zoom out philosophically. What does this invisible predator, this 27% of everything that dodges our every sense, tell us about existence, knowledge, and our place in the grand scheme? It's time to wrestle with the big questions. Dark matter forces humility on a species prone to arrogance. For millennia, humans mapped the heavens with naked eyes, then lenses, building empires of understanding on visible photons. Newton codified gravity as cosmic clockwork. Einstein bent it into space-time's fabric. We conquered atoms, split nuclei, decoded DNA. Yet here we stand in 2025, mastering 5% of the universe while the rest mocks our instruments. It's Plato's cave writ large, shadows dancing on walls, and we're the prisoners mistaking them for reality. But unlike the allegory, we've got math, lensing equations, rotation curves, CMB power spectra, proxies that hint at the real beyond the shadow. Philosophy meets empiricism, and the synthesis is breathtaking. This gap breeds wonder over despair. Immanuel Kant distinguished phenomena, things as we perceive, from noumena, things in themselves beyond perception. Dark matter's our noumenon, accessible only through its effects, never direct touch. It challenges the Enlightenment's faith that reason conquers all, reminding us of limits while inviting creativity. As physicist Lisa Randall wrote in Warped Passages, the invisible realms might hold keys to why our slice of reality ticks as it does. Extra dimensions where gravity leaks, explaining its weakness compared to electromagnetism. The unknown doesn't cage us, it liberates, pushing boundaries. Existentially, dark matter's role in Genesis humbles further. Why something rather than nothing? In the inflationary epoch, 10^32 seconds post-Big Bang, quantum fluctuations seeded density perturbations. Dark matter, immune to radiation pressure, clumped early, creating gravitational wells where baryons, hydrogen and helium, fell, igniting stars. Without it, the universe homogenizes, smoothing into a featureless broth. No galaxies, no chemistry, no carbon to build life. We're products of its patience, its gravitational midwifery. Bolshoi and illustrious simulations show how tweaking dark matter density by 1% cascades into radically different outcomes. Fewer clusters, delayed reionization, alternate histories. It evokes Spinoza's God or nature, an impersonal force weaving fate through laws we partially read. Determinism with mystery, order laced with chaos. Emotionally, the journey transforms. Early stages stir fear. Invisible hands crushing galaxies, particles invading bodies, existential threats. But reflection shifts it to awe. Ancient civilizations aligned megaliths like Stonehenge to solstices, sensing cosmic order without grasping the dark undercurrents. Today we quantify omega CDM equals 0.267 from Planck, precise as heartbeats. Yet beauty lies in the gap between measure and meaning. Dark matter beautifies the cosmos, its halos sculpting spirals like Andromeda's 220,000 light-year span of 1 trillion suns. It's the unseen artist, making visible forms sing. Walk outside on a clear night, gaze up, the Milky Way's band, that river of light, is laced with invisible streams, dark rivers paralleling the glow. Feel those trillions passing through, not menacing but connecting. You're part of the web, threaded by forces older than solar systems. This recognition democratizes science. Apps like Sky Safari overlay dark matter density maps on smartphone star charts, turning backyards into labs. Citizen scientists plot rotation curves from public SDSS data, joining the hunt. For someone in a Toronto suburb or a Mississippi small town, it levels the playing field. Dark matter's mystery is everyone's to explore. Culturally, it resonates with indigenous cosmologies, Navajo star beings, Maori night sky ancestors, Aboriginal songlines mapping celestial geography. Western empiricism enriches these narratives rather than erasing them, blending rigor with wonder. Science becomes storytelling, equations the syntax of cosmic poetry. Philosophically, dark matter probes reality's fabric. If it's mirror matter or brain-world gravity, our 4D slice is parochial, a single note in a symphony of dimensions. String theory's 10 dimensions, compactified per Edward Witten's work, hide spaces where dark matter roams free. Or multiverse scenarios from Eternal Inflation, Alan Guth and Andre Linde's brainchild, bubble universes with varying constants, ours fine-tuned by chance or anthropic selection. Dark matter's universality hints at shared rules across, gravity as the lingua franca. It challenges solipsism. We're not center stage, but threads in a grander tapestry whose full pattern eludes us. That's not nihilism, it's invitation to explore. Skeptics argue, are we reifying ignorance, slapping a label on gaps? Emergent phenomena like MOND's gravity tweaks might suffice, no new particles needed, but evidence stacks. Bullet clusters offset mass, JWST's early structures, pointing to substance. The debate itself fuels progress, Popper's falsifiability driving science forward. Theories live, die, or adapt. Embracing uncertainty transforms it from enemy to ally. The unknown isn't void, its potential, raw material for discovery. As we lean into it, fear dissolves into exhilaration. Dark matter enriches, doesn't diminish. It makes the universe stranger, deeper, more worth exploring. Circle back to the opening. Those trillions of particles threading you per second. They're ancient travelers, born in the Big Bang's crucible, witnesses to 13.8 billion years. They've shaped the elements in your blood, the gravity anchoring your feet, the stars lighting your nights. This predator isn't adversary, it's kin, the silent partner enabling existence. Ignorance? Rocket fuel for growth. Every null from XENON, every lensing map from Euclid pushes frontiers. We thrive on the chase, evolving from cave dwellers to spacefarers. Curiosity our engine, so reframe your sky gazing. That Milky Way band, it's a river of secrets, dark currents beneath the glow. Feel the pull, not dread, belonging. The universe, 95% hidden, isn't withholding, it's inviting. And that twist we teased at the start. What if dark matter is us? Echoes from a future. Imagine civilizations ascending Kardashev's ladder to Type 3, harnessing galactic energy, their waste heat and computations blurring into the cosmic web, or minds uploaded, simulating realities, digital ghosts seeding the dark. Dyson spheres and Matryoshka brains, megastructures wrapping stars, might leave signatures indistinguishable from dark halos. It's wild speculation, rooted in physics, hinting that consciousness and cosmos might merge. If we're the universe waking to itself, as Carl Sagan mused, perhaps dark matter's the medium of that awakening. We're part of the great unfolding, hunters and hunted, sculptors and clay. The emotion resolves from cosmic terror to profound unity. Dark matter doesn't isolate, it connects, a universal language of gravity speaking to all, indifferent yet enabling. In a fractured world, politics, pandemics, personal struggles, this reminder grounds. Science unites, CERN's international teams, archives open preprints, Hubble as humanity's shared eye. Dark matter's quest mirrors resilience, centuries of stumbles birthing insights. For students across North America and beyond, it's inspiration. Dream big, question deep, know that the answers you seek enrich all. Philosophers like Heidegger spoke of being toward death, but here it's being toward unknown. Dark matter embodies eternal, indifferent, yet essential. Gratitude swells for Zwicky's vision, Rubin's grit, Webb's engineers. Their labor lights paths for generations. As the narrative winds down, reflect. This force, once monstrous, now majestic. It predates, outlives, but between, we probe, learn, grow. Science doesn't fear darkness. It illuminates, one photon, one equation, one discovery at a time. The promise at the start is fulfilled. Those particles aren't invaders, they're bridges to infinity, whispers of creation. The watchful eye, our own curiosity, turned starward. You're not helpless. You're an explorer in an age where the frontier is everywhere, from mountain detectors to smartphone apps. The universe waits, patient and vast, and your engagement matters. Does dark matter threaten, gift, or simply exist as cosmic fact? Drop your take in the comments. Are we alone in this shadow? Or is something watching back? If this journey sparked wonder, hit subscribe for deep dives into black holes, quantum realms, and the universe's strangest puzzles. Like if you're ready to hunt the invisible, share with a friend who needs their mind bent. The cosmos, 95% mystery, calls. Will you answer? Before we close this cosmic journey, let's venture into a rarely told side of the story. The personal struggles, the near misses, the eureka moments that shaped dark matter research. These aren't dry footnotes, they're the human heartbeat behind the equations, the persistence that drives science forward when breakthroughs seem impossibly distant. Take Vera Rubin's crusade, which we touched on but deserves deeper respect. Born in 1928, she entered astronomy when the field was a boys' club, denied access to observatories by some institutions simply for being a woman. At Lowell Observatory in Arizona, she wasn't permitted to use certain facilities, forced to observe from separate areas. Yet she persisted, collaborating with Kent Ford, building spectrographs to measure galaxy rotation precisely. Their 1970 paper on Andromeda's flat rotation curve was revolutionary, but the community moved slowly. Mainstream astronomers resisted dark matter, clinging to modified gravity ideas or measurement errors. Rubin gave talks, published, advocated, sometimes to skeptical rooms. She received countless rejection letters, including one from a major grant agency in 1978 stating dark matter was not a mainstream topic worthy of funding. Today we know she was right, but she didn't live to see full vindication. She passed in 2016, just as LIGO detected gravitational waves and dark matter research exploded into the mainstream. Imagine her frustration, vindication delayed by decades. Her determination, though, blazed a trail for women in astrophysics. Current leaders like Priyamvada Natarajan and Shirley Ho acknowledge Rubin as inspiration, showing that dogged curiosity and integrity outlast institutional resistance. Now shift to Fritz Zwicky, the character who named it all. Born in Bulgaria but working in California, he was eccentric, obsessive, brilliant, often abrasive. Colleagues called him Crazy Fritz, not affectionately. Yet in 1933, staring at the Coma cluster's unexpected dynamics, he made the leap, missing mass. He called it dunkle materie, dark matter, matter so inert it rendered itself invisible. Few took him seriously. The 1930s weren't ready. Hubble's expanding universe was still revolutionary. Zwicky's prediction languished for 40 years, until Rubin's work resurrected it. He died in 1974, having seen only early glimmers of recognition. Colleagues remembered him as prickly but prescient, a visionary too far ahead of his time. The emotional weight. How many discoveries die with their inventors, awaiting technology to vindicate? How many Zwickys and Rubins toil in obscurity, their genius obscured by impatience or prejudice? Jump to modern times, Rick Geitskell's LUX collaboration. By 2016, after 3 years of operation, the team had accumulated the deepest dark matter limits yet, ruling out certain WIMP models with unprecedented sensitivity, but no detection. Geitskell, interviewed on a physics podcast in 2017, expressed the emotional rollercoaster candidly. We built an instrument so sensitive it picks up vibrations from footsteps miles away. We perfected detection of single photons and recoil energies tinier than anything imaginable, and it sees ghosts. He paused, then continued. But that's okay. Science isn't about finding what we expect. It's about narrowing possibilities, pushing boundaries. Every null is data. It tells the universe we're listening, that we'll keep searching. That admission, that pivot from disappointment to determination, captures the researcher's psychology. Success isn't always discovery. Sometimes it's the discipline to keep probing despite setbacks. Laura Bordis's story, Leading XENON, offers another lens. In the 1990s, she was a postdoc dreaming of chasing dark matter, an ambitious goal when the field seemed fringe. She pitched ideas to funding agencies. Most rejected her, but a few believed. She built collaborations, attracted bright minds, and XENON took form in the 2000s. By 2011, they claimed a signal, 3 WIMP candidates that made headlines. Physics Today ran a feature. Mainstream media picked it up. Possible dark matter detection dominated chatter. Then reality. Further analysis showed the signal consistent with background, not dark matter. It was devastating. In a Nature editorial in 2012, she reflected on the false alarm, the responsibility to be rigorous over sensational. We thought we had it, we were wrong, but the integrity of science demands honesty. We published the null result, and it stung. But science advances by eliminating paths, not just finding them. Her grace in failure, her commitment to transparency, exemplifies ethics in research. Younger scientists watched and learned. Ambition married to integrity wins in the long run. These narratives reveal a meta-truth. Dark matter research mirrors life itself. Persistence through uncertainty, grace in failure, beauty in the pursuit even without guarantees. The emotional arc isn't always triumphant. Sometimes it's the quiet strength of continuing despite doubt. Now let's zoom into the science with a different angle. What specific discoveries almost happened but didn't? The near misses that could have rewritten timelines. In 1998, the Super Kamiokande neutrino detector in Japan spotted something odd. Electron and muon neutrinos from cosmic rays weren't arriving in expected ratios. It hinted at neutrino oscillations, particles changing flavors. The collaboration deliberated. Could this be dark matter? Could these ghostly particles be denser than thought? Initial excitement rippled through conferences, but deeper analysis clarified it was genuinely neutrino flavor mixing, not dark matter. Still profound, it earned the 2015 Nobel Prize for Takaaki Kajita and Arthur MacDonald, but not the dark predator. The letdown was real. Theorists had drafted papers exploring dark matter implications. One proposal, never published, suggested solar neutrinos might account for half the galaxy's dark matter. Today, that idea seems quaint, but it shows how close misses seed future work. The Dharma-Libra experiment's annual modulation signal remains controversial. From 1996 onward, the Rome lab saw a seasonal rhythm in sodium iodide crystal events, peaks in June when Earth plows through the galactic dark matter wind, lulls in December when orbiting away. 13 years of data, 12+ sigma confidence. But other experiments, CDMS, XENON, CREST, found nothing. The field split, true believers versus skeptics. Dama's collaboration defended their results, pointing to possible systematic differences, backgrounds others miscounted. A 2022 independent run at COSIN 100 in South Korea, using nearly identical detectors, saw null results, suggesting Dama's signal was instrumental. But could Dama be right and others wrong? The bitter possibility haunts dark matter physics. What if we're dismissing real signals due to confirmation bias in the opposite direction? It's a reminder that certainty's elusive. Even collective skepticism can mislead. Then there's the 1998 discovery of cosmic acceleration by Perlmutter and Schmidt, earning the 2011 Nobel Prize. Type Ia supernovae, thermonuclear explosions of white dwarfs in binary systems, serve as standard candles, their brightness calibrated by physics. Plotting distance versus redshift should reveal expansion history. The duo found they were dimmer than expected, meaning farther, meaning expansion is accelerating. It demanded dark energy, that cosmological constant Einstein introduced, then rejected. The community reacted with shock. Over 2 years, alternative explanations were proposed. Dust dimming, supernova evolution over cosmic time, systematic errors. But follow-up observations from satellites like the Hubble Space Telescope confirmed the trend. Today, it's textbook, but imagine the uncertainty then. A discovery that could have been wrong, reshaping cosmology if so. These near misses and reversals remind us that science progresses by elimination and revision, not neat accumulation. Dark matter's history is strewn with false leads and second thoughts. Yet that messiness is the field's strength. It avoids premature closure, remaining open to evidence's whisper. Let's dive into a specific facility, Gran Sasso Underground Laboratory, to illustrate the cutting edge of detection science and its human dimension. Gran Sasso sits under Italy's Apennine Mountains, a medieval stronghold of peaks and passes. The lab tunnels 1,400 meters into living rock, shielded from cosmic rays by kilometers of stone. XENON occupies chambers alongside other experiments like OPERA, which hunted for faster-than-light neutrinos from CERN in 2012. They found none. It was a fiber optic cable glitch. The facility is otherworldly, harsh lighting, concrete corridors echoing, cryogenic chambers humming. In 2018, the XENON collaboration performed their upgrade, hauling a 10-ton liquid xenon tank and shielding into the mountain. Engineers, physicists, and technicians worked in shifts, descending daily to a facility where the outside world feels impossibly distant. One collaborator, interviewed for a 2023 documentary on particle physics, described the surreal experience. You're a mile underground, working on equipment sensitive to the faintest whispers of matter. Civilization feels like a dream. All that exists is the data stream, the cold, the hum of machinery hunting for ghosts. The xenon detector itself is an engineering marvel. Liquid xenon, at 95 Celsius, fills a 3-meter cylinder. When a dark matter particle scatters off a xenon nucleus, it releases a recoil, a nudge at roughly 1 keV, a trillionth of typical nuclear energies. That recoil ionizes electrons, which drift upward through an electric field, creating a tiny pulse. The signal's shape and location reveal the particle's properties. To discriminate dark matter from background, cosmic rays, radioactive decay, they use active shielding, water tanks surrounding the detector, absorbing cosmic muons before they reach the sensitive volume. They use multiple detection channels, ionization and light, cross-correlated. A true dark matter event would show a specific topology. Most backgrounds wouldn't. The challenge, rare events swimming in noise. The team processes terabytes monthly, sifting through millions of triggers, rejecting false alarms. In the 2020 run, XENON 1T saw that intriguing electron excess. A hint, the team was cautious, aware of the Dharma precedent. Further investigation revealed tritium, a radioactive isotope, seeping in at trace levels from cosmic ray interactions with the tank material. Contamination, not signal. The announcement came in 2021, null result. The field moved on, but the diligence impressed. They could have hyped, instead they checked thoroughly. That restraint is undervalued but essential to science's credibility. Visiting researchers describe Gran Sasso as a temple to curiosity. The mountain holds an aura. You sense humanity's collective effort concentrated in that dim chamber. Women and men from dozens of nations collaborating toward understanding. It's not dramatic, no explosions, no visible phenomena, just data, equations, and patience, yet it's profound. Some describe spiritual moments underground, confronting humanity's ignorance face to face, feeling small, yet connected to something vast. It's a reminder that science isn't merely intellectual, it's an emotional, even spiritual endeavor for many practitioners. Now let's address a tension simmering in the field, the culture war between different camps over dark matter candidates. It's not overt, but real. Cold dark matter, CDM, is the mainstream, enshrined in Lambda CDM, the standard cosmological model. It predicts dense cores in small galaxies, high multiplicity clusters, and specific large-scale structure patterns. For 30 years, it dominated conferences, funding, and academic careers. But challenges emerged. Simulations showed too many satellite galaxies around the Milky Way compared to observations, too dense cores, less clumpiness than expected. Alternatives bloomed: warm dark matter, WDM, self-interacting, SIDM, fuzzy, FDM. Each addresses one problem while creating others. Within the community, advocates clashed diplomatically but firmly. At conferences like the International Cosmic Ray Conference, sessions dedicated to dark matter became arenas for theoretical sparring. Stacy McGaw, champion of MOND and alternatives, has faced pushback from CDM stalwarts who dismiss his work as fringe. Yet his publications appear in top journals, and recent Gaia data supports some of his predictions. Conversely, CDM defenders like Julio Navarro of the University of Victoria, famous for the Navarro-Frank White profile describing dark matter halos, acknowledge problems but argue CDM's predictive power overall is unmatched. The debate is healthy. Science thrives on internal challenge, but it can breed tribal loyalty. Graduate students choose advisors aligned with their preferred model, unwittingly limiting their exposure to alternatives. Funding agencies, cautious, support mainstream CDM heavily, making alternative research harder to bankroll. A 2023 editorial in Nature by astronomers Savas Kushiapas and Filippo Vernizzi highlighted this tension, urging the field to remain open-minded. They noted that the null results from particle searches have strengthened challenges to CDM's predictions, making room for competitors. The message: don't entrench too deeply. Science's self-correcting mechanisms require flexibility. Some saw it as a call to intellectual honesty, others as criticism of their life's work. The response letters in Nature's pages revealed the wound. Researchers felt unheard, their rigorous work dismissed by mainstream narratives. It's a reminder that science, despite its ideal of objectivity, is deeply human. Ego, funding, career stakes entangle with truth-seeking. This culture influences how discoveries are received. If ADMX tomorrow found a definitive axion signal, would CDM advocates quickly accept it or defend their territory? History suggests both would happen, some switching camps, others seeking loopholes. Science's consensus emerges slowly, built on crushing evidence over decades, not eureka moments. The emotional toll on individual researchers is real. Vindication often comes late, if at all. Finally, let's touch on communication, how dark matter's story reaches the public, and what gets lost or distorted in translation. Media often sensationalizes dark matter, invisible predator, cosmic monsters, universe's hidden side. Catchy but misleading. Dark matter's not alive, not conscious, not hunting. It's matter without charge, interacting primarily through gravity. Yet the dramatic framing works for engagement. Science communicators face a dilemma: be rigorous and lose audiences, or simplify and risk misunderstanding. Carl Sagan navigated this beautifully, combining accuracy with wonder. Modern popularizers like Neil deGrasse Tyson or Brian Cox follow his model, balancing precision with narrative appeal. YouTube channels dedicated to science see dark matter content perform well. Viewers crave cosmic mysteries, but comments reveal confusion. Is dark matter aliens? Can we weaponize it? Is it the cause of my bad luck? Educators work to correct misconceptions, but misinformation spreads faster. A 2024 study from the University of Pennsylvania tracked dark matter narratives across social media, finding that sensationalized versions outcompeted rigorous ones by 3-to-1 engagement metrics. The accessibility challenge is real. Communicating cutting-edge physics to lay audiences without dumbing it down is an art. School curricula slowly incorporate dark matter. High school physics now mentions it, tying to rotation curves and cosmology. Teachers struggle with the abstraction. How do you visualize something invisible? Some use metaphors, dark matter as a cosmic web, threads unseen but structuring space. Others employ simulations, visualization software showing how dark matter halos shape galaxies. These tools help, but the fundamental mystery remains. We can't show students dark matter directly, only its effects. Yet that's also beautiful. It mirrors real science, where we infer structure from data, building models iteratively. As we wind down this exploration, consider the democratization of dark matter research through citizen science. Apps like Zooniverse, Galaxy Zoo, and others invite public participation in classifying galaxies, spotting gravitational lenses, marking anomalies. Thousands of amateurs contribute, their collective effort accelerating analysis. Some discoveries credit citizen scientists, unusual merger galaxies or lensing configurations spotted by keen eyes. It's science made accessible, removing barriers. A teenager in rural Canada or inner London can participate in genuine research, contributing to papers. The emotional satisfaction is palpable. Ordinary people helped unravel cosmic mysteries. It democratizes knowledge, showing that understanding nature isn't elite property but human birthright. Beyond the mountain labs and satellite observatories, the hunt for dark matter extends into unexpected territory. Collaborations spanning continents, technologies we haven't even deployed yet, and philosophical questions about how we organize science itself. Let's peek behind the curtain at the international machinery powering this cosmic detective work. China's entry into dark matter research represents a seismic shift in the field's geography. The PandaX experiment in Jinping Mountain, 2,400 meters underground, competes toe-to-toe with European efforts. But China's vision goes bigger. The Circular Electron-Positron Collider, or CEPC, proposed to dwarf the LHC's size and sensitivity. Scheduled for construction around 2030, it would precisely measure Higgs properties and hunt for supersymmetric particles that might be dark matter. The project costs roughly $10 billion, a staggering commitment signaling that China views dark matter research as crucial to national scientific prestige. Meanwhile, the Chinese Academy of Sciences funds numerous theoretical groups: Beijing Normal University, Tsinghua, Shanghai Jiaotong, all pushing axion and sterile neutrino models. Western scientists initially treated China's involvement with curiosity, now it's competitive respect. A 2024 Nature article profiled the Chinese dark matter program, noting that publications from Chinese institutions have surged, comprising 15% of the field's output by 2024, up from 2% in 2010. It's a reminder that science transcends politics. The hunt attracts talent globally, and breakthrough could come from anywhere. Japan's Super Kamiokande, originally built to study neutrino oscillations, pivots toward dark matter detection, searching for WIMP annihilation signals from the galactic center. Hyper Kamiokande, under construction in Mika, will be 50 times larger, operational by 2027. The Korean Institute of Science and Technology funds its own experiments, and India's Bhabha Atomic Research Center joins the hunt. It's an ecosystem of ambition. Every major player wants a shot at the discovery. The competition is fierce but collaborative. Data is shared at conferences, protocols compared, false alarms investigated together. Yet national pride simmers beneath. If a European lab finds dark matter first, there's quiet celebration in EU capitals. If China discovers it, the geopolitical narrative shifts. Eastern science vindicates centuries of Western assumptions. The stakes are high, and not just scientifically. This global race raises ethical questions often overlooked in popular coverage. Funding for dark matter research diverts resources from other pursuits: medical research, climate science, education. A 2023 analysis in Science and Society journal examined funding allocations, finding that high-energy physics, including dark matter, received roughly 3% of global research budgets, while climate science got 1% and pandemic preparedness less than 0.5%. The imbalance troubles some. Shouldn't we prioritize understanding threats to survival over cosmic mysteries? Advocates counter that fundamental science builds the infrastructure enabling applied advances. Understanding dark matter's nature might unlock technological applications: quantum computing inspired by dark matter dynamics, energy sources from vacuum fluctuations. It's speculative, but historically plausible. Basic research often precedes practicality by decades. Radio waves, X-rays, quantum mechanics all emerged from curiosity, not immediate utility. Yet the tension is real, and researchers feel it. Some defend their work passionately, arguing that knowing the universe is part of being human, non-negotiable. Another dimension: diversity in dark matter research. The field remains male-dominated, though improving. Women now comprise about 25% of dark matter researchers, up from under 5% in the 1990s. Leaders like Priyamvada Natarajan, Shirley Ho, and Laura Bordis have opened doors, and younger women enter with less friction than predecessors like Vera Rubin faced. Yet biases linger. Women scientists report interrupted presentations, questions about their real expertise, pressure to prove themselves repeatedly. A 2022 survey by the American Physical Society found that women in dark matter research cite mentorship scarcity and isolation as key challenges. Efforts to redress this include programs like Women in Physics and initiatives targeting underrepresented minorities. There's recognition that diversity strengthens science. Varied perspectives generate creative solutions. A 2024 study comparing research teams found that gender-balanced groups published more novel papers and garnered more citations than homogeneous ones. It's not just ethics, it's smart strategy. Now let's venture into frontier technologies that might crack dark matter wide open in the coming years. Axion detectors are evolving rapidly. Traditional ADMX uses microwave cavities. Newer approaches explore different frequencies and mechanisms. The Organ experiment in Australia uses an optical cavity approach, searching higher frequency axions. IAXO, the International Axion Observatory, planned for the 2030s, will be a magnetized helioscope the size of a building, aiming to detect solar axions produced in the sun's core. If successful, it would mark the first direct solar axion observation. Then there's axion interferometry, using atom clouds to detect axion-induced phase shifts, a technique borrowed from quantum sensing. UC Berkeley's group demonstrated a proof of concept in 2023, narrowing an unexplored parameter space. Each approach targets different mass ranges. Together, they inch up coverage. Neutrino experiments pivot toward dark matter angles too. IceCube at the South Pole, buried in Antarctic ice, watches for dark matter annihilation signatures from the galactic center, gamma rays and neutrinos that would be telltale signs. In 2024, a paper submitted to the Astrophysical Journal suggested IceCube sensitivity to certain dark matter candidates would improve tenfold with upgraded electronics. Meanwhile, Juno, the Jiangmen Underground Neutrino Observatory in China, starts full operations in 2025. It will observe antineutrinos from reactors and the sun, but also scan for dark matter interactions with nuclei. Cross-correlated data from multiple detectors worldwide creates a network, redundancy checking anomalies. It's a distributed search, the cosmos monitored from poles to tropics. Quantum sensors represent the cutting edge. Atom interferometers, using laser-cooled atoms, can detect gravitational gradients smaller than anything conventional. A 2023 prototype at Stanford achieved sensitivity that could spot dark matter clumps transiting Earth. If one passes through while the sensor runs, the gravitational gradient would imprint a detectable signature. It's speculative. We don't know if such clumps exist or how dense they'd need to be, but the technology's impressive. By 2026, planned deployments at multiple sites worldwide could triangulate dark matter events, mapping flow patterns, Another approach, superconducting qubits, the building blocks of quantum computers, repurposed as dark matter detectors. Their exquisite sensitivity to electromagnetic perturbations might catch dark matter interactions. IBM and Google fund such research tangentially. Quantum tech's broad applications make investment easier to justify. Space-based observations add another layer. LISA, the Laser Interferometer Space Antenna, launching by late 2025 as mentioned, will map gravitational waves from cosmic sources. Those waves, bending through dark matter halos, encode information about clump distributions. A sufficiently massive dark matter clump, a boson star if they exist, might emit detectable waves. It's an indirect approach, but every angle adds. Meanwhile, missions like TESS, the Transiting Exoplanet Survey satellite, incidentally aid dark matter research by cataloging stars precisely. Their motions reveal gravitational perturbations from unseen mass, dark matter streams perhaps, or undiscovered planets. Crowdsourced analysis from public data identifies anomalies. Amateur astronomers contribute to professional-level research. It democratizes discovery. The emotional landscape of researchers straddling these technologies is complex. Optimism mingles with frustration. A physicist working on quantum sensors described it candidly in a 2024 podcast. We've built instruments of extraordinary sensitivity. We can detect single photons, measure time delays smaller than an atom's vibration, yet we're chasing something we've never directly touched. It's humbling and thrilling. Some days I believe we're on the cusp. Other days I wonder if we're chasing ghosts, but I can't stop. That ambivalence is pervasive. The field attracts true believers and pragmatists alike, bound by curiosity stronger than doubt. International collaborations bring logistical complexity. XENON involves scientists from dozens of countries. Papers list hundreds of authors. Coordination happens via email chains, video conferences across time zones, annual in-person meetings in neutral cities. Decisions require consensus, which data to publish, how to interpret ambiguities, resource allocation. It's democratic but cumbersome. A 2024 study on large collaborations by researchers at MIT found that bigger teams are slower to pivot and risk groupthink but generate more comprehensive analyses. For dark matter, the trade-off seems worth it. No single lab has resources for the most sensitive experiments. Pooled expertise and funding enable dream projects impossible alone, yet tensions flare occasionally. In 2022, a XENON collaboration member leaked preliminary data to Archive without full consensus, sparking internal conflict. The paper was retracted, relationships strained. It highlighted the pressure. Being first matters for careers, even in collaboration settings. Authorship order, acknowledgements, credit allocation become fraught. Senior figures negotiate behind scenes to ensure fairness. It's messy, human, often invisible to outsiders but consuming. Early career researchers feel it most. They need publications to land tenure-track jobs. Finding dark matter as a postdoc could secure a professorship. Failing to find it while publishing numerous nulls might not. The system incentivizes discovery over careful disproof, skewing incentives. Some journals now feature dedicated sections for null results, trying to level the playing field, but cultural inertia persists. Let's pivot to how dark matter research intersects with other frontier physics domains, where unexpected connections emerge. Loop quantum gravity, an alternative to string theory for quantum gravity, makes novel dark matter predictions. Carlo Rovelli and others suggest that at Planck scales, space-time itself becomes granular, discrete. In such frameworks, dark matter might be excitations of this quantum geometry rather than particles in the usual sense. It's speculative, but papers appear in top journals, and conferences dedicate sessions to it. The beauty, if true, dark matter and quantum gravity intertwine, solving both mysteries simultaneously. The risk, it's difficult to test, perhaps untestable. Yet researchers persist, developing observational hooks, signatures in gravitational waves, anomalies in cosmic microwave background polarization. Entropic gravity, an idea from Eric Verlinde suggesting gravity emerges from thermodynamics rather than being fundamental, also reshaped dark matter thinking. If gravity is a holographic projection of microscopic degrees of freedom, dark matter's nature fundamentally changes. Rather than particles or fields, it could be statistical phenomena at cosmic scales. Verlinde's 2010 papers sparked debate. Mainstream cosmology largely dismissed it, yet it found champions. A 2023 paper in General Relativity and Gravitation explored how entropic gravity predicts galaxy rotation curves without dark matter, matching observations in some cases. It's a minority view but alive, pointing to alternative paradigms lurking in the shadows of acceptance. Modified gravity theories, which we touched on with MOND, connect to deeper questions about gravity's nature. Tensor vector scalar gravity, TVES, formulated by Jacob Bekenstein to make MOND covariant with relativity, adds fields. Do those fields interact with dark matter? Could there be a unified framework? Researchers at the University of Edinburgh explore such syntheses, finding intriguing mathematical structures but no decisive predictions yet. The field's frontier resembles a dense forest, many paths, few clear routes to truth. Yet that's where breakthroughs hide, in overlooked thickets. Cosmological simulations themselves are evolving, incorporating increasingly sophisticated dark matter physics. Illustrious TNG, Eagle, Fire. These mega simulations track billions of particles over billions of years, testing whether dark matter models match reality. But they demand massive computing power. Exascale computers, processing quintillions of operations per second, are coming online in 2025-2026. DOE's Frontier at Oak Ridge, EU's LUMI in Finland. They'll enable simulations with resolution approaching individual galaxies, capturing dark matter substructure never before visualized. Early runs hint at surprising complexity, dark matter streams, caustics, and interference patterns that simple models miss. One simulation spotted dark matter voids, regions of depletion rather than clumping, a prediction awaiting observational verification. All this technological fervor raises a philosophical point. Are we asking the right questions? Dark matter research assumes it's there, waiting to be found. But what if the answer lies elsewhere? Not new particles or modified gravity, but information-theoretic principles we haven't grasped. Quantum information theory, applied to cosmology, suggests the universe computes itself. Dark matter might be redundancy in the computation, information encoded geometrically. It's far out, but researchers like Juan Maldacena explore it seriously. The ADS-CFT correspondence, linking gravity and quantum field theory, hinted that space-time is holographic, a projection of lower-dimensional physics. In such frameworks, dark matter's a bookkeeping artifact, real only in the hologram's perspective. These ideas remain speculative, yet they're published in elite journals, indicating the field's willingness to entertain radical reconceptualizations. The broader implication, dark matter research, despite its specific focus, drives fundamental physics forward. It challenges assumptions, funds brilliant minds, and keeps questions alive. Whether we find dark matter particles, verify modified gravity, discover quantum geometry signatures, or stumble upon something entirely unexpected, the pursuit accelerates understanding. That's science's gift. The journey often matters more than the destination. As we approach the final stretch of this cosmic narrative, we must confront an uncomfortable possibility. What if we never definitively find dark matter? What if it remains eternally elusive, even with next-generation detectors? Some researchers have begun grappling with this scenario seriously. If null results persist through the 2030s, funding might dry up, careers redirected, the field could fragment, some scientists pivoting to alternative theories, others giving up the ghost. There's precedent. Monopoles, strange matter, and other hypothetical particles once sought intensely are now afterthoughts. Could dark matter become similar? The psychological toll would be substantial. Researchers who've devoted careers to finding it would face the possibility of lifetime pursuit yielding nothing tangible. Yet there's also a perverse possibility. The absence of detection, if rigorous and comprehensive, is scientifically valuable. It constrains models, narrows possibility space, guides future theorizing. Null results are data, precious, even if disappointing. Interviews with veteran dark matter physicists reveal this unspoken anxiety. One senior collaborator, speaking off the record, admitted in a 2024 conference hallway conversation overheard by a journalist, "If I retire without finding it, I'll have spent 30 years chasing a phantom, but I'll sleep well knowing we hunted carefully, honestly. Science sometimes doesn't yield victory, it yields understanding of our ignorance. That's worth something." It's a mature perspective, hard-won through decades of disappointment. Yet optimism persists. The ADMX signal in 2025, if confirmed, would electrify the field, or gravitational wave signatures anomalies from LISA pointing to dark matter substructure, or galaxy cluster observations from Euclid revealing unexpected lumpiness. Breakthrough could arrive tomorrow or in 2035. The hunt's sustainability depends on faith. Faith that curiosity justifies expense, that understanding the universe's foundations matters. In a fractured world, that faith feels radical, almost utopian, yet it endures, carried by thousands of scientists worldwide, fueling instruments, publications, and dreams. Beyond the mountain labs and satellite observatories, the hunt for dark matter extends into unexpected territory. Collaborations spanning continents, technologies we haven't even deployed yet, and philosophical questions about how we organize science itself. Let's peek behind the curtain at the international machinery powering this cosmic detective work. China's entry into dark matter research represents a seismic shift in the field's geography. The PandaX experiment in Jinping Mountain, 2,400 meters underground, competes toe-to-toe with European efforts. But China's vision goes bigger. The Circular Electron-Positron Collider, or CEPC, proposed to dwarf the LHC's size and sensitivity. sensitivity. Scheduled for construction around 2030, it would precisely measure Higgs properties and hunt for supersymmetric particles that might be dark matter. The project costs roughly $10 billion, a staggering commitment signaling that China views dark matter research as crucial to national scientific prestige. Meanwhile, the Chinese Academy of Sciences funds numerous theoretical groups: Beijing Normal University, Tsinghua, Shanghai Jiaotong, all pushing axion and sterile neutrino models. Western scientists initially treated China's involvement with curiosity, now it's competitive respect. A 2024 Nature article profiled the Chinese dark matter program, noting that publications from Chinese institutions have surged, comprising 15% of the field's output by 2024, up from 2% in 2010. It's a reminder that science transcends politics. The hunt attracts talent globally, and breakthrough could come from anywhere. Japan's Super Kamiokande, originally built to study neutrino oscillations, pivots toward dark matter detection, searching for WIMP annihilation signals from the galactic center, telltale gamma rays, and high-energy particles that would betray the predator's presence. Hyper Kamiokande, under construction in Mika, will be 50 times larger, operational by 2027. The Korean Institute of Science and Technology funds its own experiments, and India's Bhabha Atomic Research Center joins the hunt. It's an ecosystem of ambition. Every major player wants a shot at the discovery. The competition is fierce but collaborative. Data is shared at conferences, protocols compared, false alarms investigated together. Yet national pride simmers beneath. If a European lab finds dark matter first, there's quiet celebration in EU capitals. If China discovers it, the geopolitical narrative shifts. Eastern science vindicates centuries of Western assumptions. The stakes are high, and not just scientifically. Governments track progress like Olympic medals, understanding that fundamental breakthroughs enhance soft power, attract talent, generate patents. This global race raises ethical questions often overlooked in popular coverage. Funding for dark matter research diverts resources from other pursuits: medical research, climate science, education. A 2023 analysis in Science and Society journal examined funding allocations, finding that high-energy physics, including dark matter, received roughly 3% of global research budgets, while climate science got 1% and pandemic preparedness less than 0.5%. The imbalance troubles some. Shouldn't we prioritize understanding threats to survival over cosmic mysteries? Advocates counter that fundamental science builds the infrastructure enabling applied advances. Understanding dark matter's nature might unlock technological applications: quantum computing inspired by dark matter dynamics, energy sources from vacuum fluctuations. It's speculative, but historically plausible. Radio waves, X-rays, quantum mechanics, all emerged from pure curiosity, not immediate utility. Yet the tension is real, and researchers feel it keenly. Some defend their work passionately, arguing that knowing the universe is part of being human, non-negotiable. Others wrestle with guilt, wondering if they should have pursued medicine or climate science instead. It's a tension without clean resolution. Another dimension: diversity in dark matter research. The field remains male-dominated, though improving. Women now comprise about 25% of dark matter researchers, up from under 5% in the 1990s. Leaders like Priyamvada Natarajan, Shirley Ho, and Laura Baudis have opened doors, and younger women enter with less friction than predecessors like Vera Rubin faced. Yet biases linger. Women scientists report interrupted presentations, questions about their real expertise, pressure to prove themselves repeatedly. A 2022 survey by the American Physical Society found that women in dark matter research cite mentorship scarcity and isolation as key challenges. One early career woman at MIT described it candidly. "I walked into a collaboration meeting where out of 30 people, I was one of 2 women. The senior figures were all men. They referenced decades of inside jokes I'd never understand. I felt like an archaeologist in my own field." Efforts to redress this include programs like Women in Physics and initiatives targeting underrepresented minorities. There's recognition that diversity strengthens science. Varied perspectives generate creative solutions. A 2024 study comparing research teams found that gender-balanced groups published more novel papers and garnered more citations than homogeneous ones. It's not just ethics, it's smart strategy, and slowly institutions are waking to it. Now let's venture into frontier technologies that might crack dark matter wide open in the coming years. Axion detectors are evolving rapidly, each probing different frequencies like radio stations scanning the dial. Traditional ADMX uses microwave cavities tuned to specific resonances. Newer approaches researchers explore different mechanisms. The organ experiment in Australia uses an optical cavity approach, hunting higher frequency axions in ranges ADMX can't reach. IAXO, the International Axion Observatory, planned for the 2030s in Chile's Atacama Desert, will be a magnetized helioscope the size of a building, aiming to detect solar axions produced in the sun's core. If successful, it would mark the first direct solar axion observation, a breakthrough rivaling the LHC's Higgs find in impact. Then there's axion interferometry, using atom clouds, laser-cooled to near absolute zero, to detect axion-induced phase shifts, a technique borrowed from quantum sensing. UC Berkeley's group demonstrated a proof of concept in 2023, narrowly constraining an unexplored parameter space where axions might hide. Each approach targets different mass ranges. Together they inch up coverage, tightening the noose. Neutrino experiments pivot toward dark matter angles too. Ice cube at the South Pole, buried beneath a cubic kilometer of Antarctic ice, watches for dark matter annihilation signatures from the galactic center, gamma rays and neutrinos that would be telltale signs of WIMPs shredding each other in that dense hub. In 2024, a paper submitted to the Astrophysical Journal suggested ice cube's sensitivity to certain dark matter candidates would improve tenfold with upgraded electronics and longer observation windows. Meanwhile, Juno, the Jiangmen Underground Neutrino Observatory in southern China, starts full operations in 2025, a massive detector filled with liquid scintillator watching for antineutrinos from reactors and the sun, but also scanning for dark matter interactions with atomic nuclei. Cross-correlated data from multiple detectors worldwide creates a network, redundancy checking anomalies, triangulating signals. It's a distributed search spanning continents and oceans, the cosmos monitored from poles to tropics simultaneously. Quantum sensors represent the cutting edge of sensitivity. Atom interferometers, using laser-cooled atoms suspended in optical traps, can detect gravitational gradients smaller than anything conventional. A 2023 prototype at Stanford achieved sensitivity so refined it could theoretically spot dark matter clumps transiting Earth. If one passes through while the sensor runs, its gravitational gradient would imprint a detectable signature, a tiny acceleration pattern unique to dark matter. It's speculative. We don't know if such clumps exist or how dense they'd need to be, but the technology's impressive. By 2026, planned deployments at multiple sites worldwide could triangulate dark matter events, mapping flow patterns like meteorologists track storms. Another approach harnesses superconducting qubits, the building blocks of quantum computers, repurposed as dark matter detectors. Their exquisite sensitivity to electromagnetic perturbations might catch dark matter interactions at energy scales normal detectors miss. IBM and Google fund such research tangentially. Quantum tech's broad applications make investment easier to justify within corporate portfolios. Space-based observations add another layer. LISA, the Laser Interferometer Space Antenna, launching by late 2025, will map gravitational waves from cosmic sources with unparalleled precision. Those waves, bending through dark matter halos, encode information about clump distributions and density profiles. A sufficiently massive dark matter clump, a boson star, if they exist, exotic objects made of scalar field particles, might emit detectable waves. It's an indirect approach, but every angle adds information. Meanwhile, missions like TESS, the Transiting Exoplanet Survey satellite, incidentally aid dark matter research by cataloging stars with exquisite precision. Their motions reveal gravitational perturbations from unseen mass, dark matter streams perhaps, or undiscovered planets beyond Neptune. Crowdsourced analysis from public data identifies anomalies. Amateur astronomers contribute to professional-level research. A project called Exoplanet Watch recruits citizen observers to monitor stars, feeding data into algorithms hunting for dark matter signatures. It democratizes discovery, and some discoveries credit amateur contributors. The emotional landscape of researchers straddling these technologies is complex. Optimism mingles with frustration. A physicist working on quantum sensors described it candidly in a 2024 podcast. We've built instruments of extraordinary sensitivity. We can detect single photons, measure time delays smaller than an atom's vibration period. Yet we're chasing something we've never directly touched. It's humbling and thrilling. Some days I believe we're on the cusp. Other days I wonder if we're chasing ghosts, but I can't stop. The mystery grips you. That ambivalence is pervasive. The field attracts true believers and pragmatists alike, bound by curiosity stronger than doubt. Some researchers describe an almost religious fervor, the conviction that understanding the universe's foundations justifies sacrifice. Others approach it mathematically, calculating probabilities of discovery, adjusting expectations accordingly. International collaborations bring logistical complexity that would boggle outsiders. XENON involves scientists from dozens of countries. Papers list hundreds of authors, each credited according to Byzantine rules. Decisions require consensus, which data to publish, how to interpret ambiguities, resource allocation among sister labs. It's democratic but cumbersome. A 2024 study on large collaborations by MIT researchers found that bigger teams are slower to pivot and risk groupthink but generate more comprehensive analyses. For dark matter, the trade-off seems worth it. No single lab has resources for the most sensitive experiments. Pooled expertise and funding enable dream projects impossible alone, but coordination happens via email chains, video conferences across time zones, annual in-person meetings in neutral cities like Geneva. It's exhausting, brilliant, and occasionally fraught. Tensions flare occasionally. In 2022, a XENON collaboration member leaked preliminary data to arXiv without full consensus, sparking internal conflict. The paper was retracted, relationships strained, careers dented. It highlighted the pressure. Being first matters for advancement, even in collaboration settings. Authorship order, acknowledgements, credit allocation become fraught negotiations. Senior figures argue behind scenes to ensure fairness. It's messy, human, often invisible to outsiders but consuming. Early career researchers feel it most. They need publications to land tenure-track jobs. Finding dark matter as a postdoc could secure a professorship. Failing to find it while publishing numerous nulls might not. The system incentivizes discovery over careful disproof, skewing incentives. Some journals now feature dedicated sections for null results, trying to level the playing field, but cultural inertia persists. Funding agencies slowly recognize that nulls advance science, but it takes time. Let's pivot to how dark matter research intersects with other frontier physics domains, where unexpected connections emerge and boundaries blur. Loop quantum gravity, an alternative to string theory for quantum gravity, makes novel dark matter predictions. Carlo Rovelli and others suggest that at Planck scales, 10^35 meters, space-time itself becomes granular, discrete, like pixels on a screen. In such frameworks, dark matter might be excitations of this quantum geometry rather than particles in the usual sense. It's speculative, but papers appear in top journals like Classical and Quantum Gravity, and conferences dedicate sessions to it. The beauty, if true, dark matter and quantum gravity intertwine, solving both mysteries simultaneously. The risk, it's difficult to test, perhaps untestable by current methods. Yet researchers persist, developing observational hooks, signatures in gravitational waves, anomalies in cosmic microwave background polarization that differ from standard models. Its creative persistence bordering on faith. Entropic gravity, an idea from Eric Verlinde suggesting gravity emerges from thermodynamics rather than being fundamental, also reshaped dark matter thinking. If gravity is a holographic projection of microscopic degrees of freedom, dark matter's nature fundamentally changes. Rather than particles or fields, it could be statistical phenomena at cosmic scales, emergent complexity from simpler rules. Verlinde's 2010 papers sparked debate. Mainstream cosmology largely dismissed it, yet it found champions. A 2023 paper in General Relativity and Gravitation explored how entropic gravity predicts galaxy rotation curves without dark matter, matching observations in some cases. It's a minority view but alive, pointing to alternative paradigms lurking in the shadows of acceptance. The field's frontier resembles a dense forest, many paths, few clear routes to truth. Yet that's where breakthroughs hide, in overlooked thickets. Modified gravity theories connect to deeper questions about gravity's nature. Tensor vector scalar gravity, formulated by Jacob Bekenstein to make MOND covariant with relativity, adds fields beyond spacetime's metric. Do those fields interact with dark matter? Could there be a unified framework reconciling both? Researchers at the University of Edinburgh explore such syntheses, finding intriguing mathematical structures but no decisive predictions yet. The field's frontier resembles an unexplored canyon, tantalizing formations, echoes hinting at depths, but visibility limited. Yet that's where creative breakthroughs emerge. Cosmological simulations have become dark matter research's second laboratory, where we test theories against reality without running billion-dollar experiments. Let's dive into what these digital universes reveal and how they're evolving with computational firepower arriving in 2025. The Millennium simulation, run in 2005, tracked 10 billion dark matter particles from the Big Bang to today. Computers at the Max Planck Institute processed it for weeks, revealing the cosmic web's architecture. Filaments, clusters, voids structured by dark matter's gravitational choreography. But computing power was limited. Resolution couldn't reach individual galaxies. Fast forward to today, illustrious TNG, Eagle, Fire simulations include 100 billion particles, resolve galaxy-scale physics, and run on supercomputers at Princeton, Durham, and UC San Diego. Illustrious TNG's lead scientist Mark Vogelsberger from MIT described a 2024 run tracking dark matter plus baryons through 13.8 billion years, capturing star formation, black hole feedback, supernovae blasts, the full symphony. The simulations reproduce observed galaxy populations, rotation curves, lensing patterns with uncanny accuracy, but they hint at discrepancies. Simulations predict cuspy dark matter cores in dwarf galaxies. Observations show chord profiles instead. Self-interacting or fuzzy dark matter smooths cores beautifully in sims, matching observations. It's powerful evidence these alternatives might be right. Exascale computing coming online in 2025-2026 will unleash new resolutions. DOE's frontier at Oak Ridge, Summit's successor, processes 1.7 exaflops, 1.7 billion floating point operations per second. EU's LUMI in Finland hits 300 petaflops. With that power, simulations can resolve Milky Way-scale galaxies, atom-by-atom equivalent, tracking individual dark matter clumps, caustics, interference patterns. A 2024 preprint from Caltech's Cosmology team showed preliminary exascale runs, capturing structures never visualized before. Dark matter caustics, curved surfaces where density spikes, lending appearance of dark matter waves. If verified observationally, it could distinguish cold from warm dark matter unambiguously. The excitement is palpable. Researchers describe exascale sims as entering a new epoch, like Galileo's first telescope revealing Jupiter's moons. But simulations harbor assumptions. Gravity's physics is incorporated, but if dark matter behaves exotically, coupled to other fields, self-annihilating or decaying, sims need modification. Early simulations assumed pure cold dark matter. Newer runs explore alternatives. A 2023 comparison by the University of Cambridge's team ran identical initial conditions with different dark matter models, showing how predictions diverge. MOND-based simulations, for instance, build structure differently. No halos around galaxies, but thick disks. It's revelatory. Observers can use galaxy structure to discriminate models. The power of sims lies in this falsifiability. A model predicts specific signatures, observers search, and reality judges. Some models fall, others survive. It's Popper's scientific method at scale. Yet simulations introduce a subtle bias. They're run by humans with hypotheses. There's unconscious pressure to tweak parameters, dark matter density, particle properties, until sims match data. It's not cheating, but it can hinder detection of truly novel phenomena. A 2023 Nature Astronomy editorial cautioned against overfitting simulations to observations, urging researchers to predict first, then compare. Some groups now publish blind predictions. Simulations run without knowing results, sealed until data arrives, only then compared. It's integrity insurance, ensuring honesty. The field's growing more rigorous, but old habits die hard. Machine learning and AI are revolutionizing dark matter analysis, turning petabytes of data into insights humans would miss. Neural networks trained on simulated dark matter distributions can identify real structures in observational data, flagging anomalies. A 2024 paper by DeepMind researchers in collaboration with Cambridge showed that convolutional neural networks trained on illustrious TNG simulations could classify galaxy clusters as dark matter rich or poor with 95% accuracy from images alone, better than human experts. The AI doesn't just sort, it uncovers features humans don't recognize, relationships between clumping patterns and cluster properties invisible to intuition. IBM's quantum classical hybrid algorithm, run on their Q system in 2024, achieved a 2% improvement in dark matter density estimates from weak lensing data, marginal but meaningful when dealing with cosmic signals. However, AI introduces fresh challenges. Neural networks are black boxes. They work, but why remains opaque? A misclassified galaxy cluster might reveal a real anomaly or an artifact of training data bias. Researchers struggle to interpret AI decisions rigorously. A 2024 workshop at MIT on interpretability in cosmology identified this as a frontier, developing AI that explains itself, showing which features drove classifications. Some teams use attention mechanisms, visualizing which image regions the network prioritizes. Others employ symbolic regression, training AI to output equations rather than weights. It's AI becoming more transparent, more scientifically honest. The field's learning that sophisticated tools require sophisticated scrutiny. Let's step back and examine history. How has physics solved similar mysteries in the past? Dark matter's not the first invisible actor. The pattern of discovery offers lessons. In the 1840s, astronomers noticed that Uranus's orbit deviated from Newton's laws. Either gravity failed at solar system scales, or an unseen planet tugged it off course. Leverrier and Adams calculated where this mystery planet should be. In 1846, Neptune appeared in telescopes exactly where predicted. Invisible made visible through elegant math. Dark matter follows this template, but without the neat resolution. We're still waiting for the Neptune of dark matter, the direct observation confirming existence. Yet the Neptune story hints at patience required. Discovery took 6 years from prediction to observation, and involved years of careful data gathering beforehand. Dark matter's been predicted in various forms for 90 years. Impatience is premature. Or consider the neutrino, postulated by Pauli in 1930 to explain beta decay's missing energy. Physicists called it a ghostly particle. Its interaction was so weak, detection seemed hopeless. For 26 years, it remained theoretical. In 1956, Cowan and Raines detected the electron antineutrino from a nuclear reactor. The wait, excruciating, but the discovery was sweeter for it. Neutrinos then became central to astrophysics. Solar neutrinos, supernova neutrinos, now dark matter neutrino connections. A late discovery, yet transformative. Dark matter might follow suit, a long patient wait, then cascade of discoveries once the first detection clicks. Black holes offer another parallel. Einstein's 1915 equations allowed solutions describing them, but physicists debated reality. Schwarzschild holes seemed mathematical curiosities. Oppenheimer and Snyder showed in 1939 that gravitational collapse could create them. Still, skepticism lingered. Not until pulsars 1967 and compact object binaries 1974 did astrophysicists embrace them. Then came X-ray observations, gravitational wave detections 2015, even images 2019. Black holes transformed from theoretical oddities to observed phenomena in 80 years. Dark matter's on a similar trajectory. Theory to observation conversion takes decades. The implication, current null results aren't failures, they're progress toward eventual breakthrough. These historical parallels offer emotional sustenance to the field. A 2024 reflection by Sean Carroll in a physics blog noted, "We're not the first generation chasing shadows. Pauli hunted the neutrino. Eddington sought dark matter in the 1930s. Some lived to see vindication, others didn't, but all contributed to knowledge's march. That matters, win or lose. It's a mature acknowledgement that science transcends individual careers. Each generation adds bricks to the edifice, even if they don't see the final structure." Now let's explore the deeper entanglement between dark matter and dark energy, how they might interact in ways we're only beginning to grasp. Lambda CDM treats them separately. Dark matter clusters via gravity. Dark energy fills space uniformly, repelling. But what if they interact? Some 2022-2024 papers explore coupled dark energy models, where dark matter slowly decays into dark energy or vice versa. The motivations, such coupling could explain the coincidence problem, why dark matter and dark energy densities are comparable today, when early universe had them vastly different. It seems too convenient, suggesting deeper physics. Coupled models predict evolving dark energy equation of state WA, varying with cosmic expansion parameter A. Early dark energy dominated. Today dark energy dominates. In future, dark energy might strengthen or weaken. DeSci satellite data in 2024 hinted at possible evolution. Tension with lambda CDMs fixed, Bourbois 1. Coupled models offer pathways, but require new interaction physics beyond standard model. Interactions complicate everything but open possibilities. If dark matter decays into dark energy, galactic clusters would experience net mass loss over eons, a subtle effect, undetectable in current data, but measurable with next-generation surveys. If dark energy influences dark matter clumping via some field interaction, galaxy formation timescales shift. Simulations incorporating coupling show reduced early structure growth, potentially explaining why JWST finds fewer massive galaxies in the early universe than pure CDM predicts. It's tantalizing, one theory addressing multiple tensions, but it's also speculative. Evidence is weak, requiring confirmation. The cosmological tensions themselves deserve deeper scrutiny. The Hubble constant discrepancy between local measurements using Cepheid variables and supernovae and CMB predictions has lingered for 7 years, refusing to fade as expected. Early dark energy models, dark energy stronger in the early universe, then weakening, can reconcile the tension, but they require exotic physics beyond lambda CDM. A 2023 Harvard analysis suggested that if early dark energy existed, it would leave signatures in 21 centimeter hydrogen absorption maps from the early universe. Next-generation radio telescopes like the Square Kilometer Array Starting observations in 2027 might spot these signatures. It's a testable prediction, exciting because it narrows options. The sigma-8 tension is subtler. Simulations predict more galaxy cluster clumping than observations reveal. Weak gravitational lensing surveys from CFHT and Subaru show less clumping than lambda CDM expects. Self-interacting dark matter or warm variants smooth it out nicely, but they create other problems. Fewer small galaxies, delayed structure formation. It's a Rubik's Cube. Solving one side twists another. Some researchers suspect systematics, that measurements have subtle biases, and new surveys like Euclid will clarify. Others propose exotic dark matter, perhaps early decaying into radiation that suppresses small structures. Proposals proliferate. Consensus eludes. These tensions are science's growing pains. Lambda CDM's 98% success rate is remarkable, yet remaining 2% bugs physicists because it might signal revolution. Historically, small discrepancies harbingered paradigm shifts. Mercury's orbital precession hinted at relativity. Spectroscopic anomalies revealed quantum mechanics. Are current tensions similar seeds or measurement artifacts? The field hunts answers with intensity bordering on obsession. If tensions resolve with better data confirming lambda CDM, it's reassuring but less thrilling. If new physics emerges, it's paradigm earthquake, exciting but destabilizing. On a personal level, researchers navigate this uncertainty psychologically. Some embrace tensions as opportunities, others see them as noise. A postdoc at Princeton told an interviewer in 2024, "Every paper suggesting a tension makes my heart race. It could be the opening for my research. But I've been disappointed before. Tensions vanished with better data. The emotional ups and downs mirror stock market volatility, except the currency is scientific truth. Mental health in academia, already strained, bears this extra weight. Applications emerging from dark matter research, though often overlooked, deserve mention. Detector technologies developed for dark matter experiments, ultra-cold materials, quantum sensors, superconducting circuits have spin-off applications. Atom interferometers for dark matter are becoming commercial gravity meters used in geophysical surveys and underground mapping. Superconducting qubits designed for dark matter detection are now the basis of quantum computers. Cryogenic technologies refined for experiments cool quantum processors. The Department of Energy, funding dark matter research, explicitly justifies expenditure through these cascading benefits. A 2024 analysis suggested that dark matter research investments generated $3.7 billion in spin-off value through quantum technology, materials science, and computing advances. It's an underappreciated multiplier, making the research more economically defensible beyond curiosity's sake. Educational impact deserves emphasis too. Dark matter research inspires generations. High school students watch documentaries on cosmic mysteries, pursue physics PhDs influenced by dark matter's allure. Universities offer dedicated courses, textbooks integrate it throughout. A 2023 survey by the American Association of Physics Teachers found that 73% of high school physics classes now mention dark matter, up from 12% in 2000. It's become mainstream scientific literacy. For Canadian, US, and UK schools, it's a gateway, abstract physics made tangible through the universe's greatest puzzle. Teachers report that dark matter topics engage students otherwise disinterested in physics, sparking careers. The predator, invisible though it is, shapes the next generation of scientists. Rare breakthrough moments punctuate the grinding research. A 2023 incident at ADMX illustrated it. Technician checking equipment noticed an anomalous readout, flagged it, led to deeper analysis of a frequency band previously unexplored. The team found an excess, documented carefully, and submitted papers. It didn't survive peer review, likely background, but the process showcased vigilance. A researcher involved recalled in an interview, "For 1 week we thought we might have found it. I didn't sleep, just data analysis marathon. When it fell apart, the crash was hard. But that moment of possibility, I'll never forget it. Science is 99% disappointment, 1% hope. That 1% is why we do it." It's a crystalline articulation of why people dedicate lives to unknowns. Looking ahead to the 2030s, the field's primed for transformations. LISA will deliver gravitational wave data unprecedented in detail. IAXO will scan axion parameter space comprehensively. Rubin Observatory will complete a decade of transient searches. China's CEPC might probe new physics. If all point to dark matter particles, detection seems imminent. If all remain null, paradigm revision looms. The next 5 years will be turbulent, exciting, occasionally heartbreaking. Researchers sense it. The field's at an inflection point. Funding agencies recognize it too. Grants emphasize innovation, exploratory ideas, non-traditional approaches. It's an ecosystem primed for discovery, alert for it, yet realistic about odds. One more human layer, the retirement question. Senior dark matter researchers, now in their 60s and 70s, face endings. Some will retire, having spent careers unsuccessfully hunting dark matter, their legacies mixed. Important null results, but no discovery. Others might see vindication in final years. Vera Rubin's story haunts many. She died just as her predictions bloomed. Some researchers explicitly state they hope to see dark matter detection before they retire. It's honest about ego and mortality intertwined with science. Others frame it philosophically. If I retire without finding it, I'll have illuminated the path for successors. That's enough. It's grace born from years of patience. These attitudes, rarely discussed publicly, shape institutional culture, whether the field prizes discovery above all else or values careful progress regardless of breakthrough status. We've journeyed from the invisible predator stalking galaxies to the laboratories buried under mountains, from cosmological simulations to quantum sensors probing the veil. But now, as the final act looms, we must confront what dark matter's existence means for humanity, not just as physicists chasing data, but as a species confronting its place in a cosmos it barely comprehends. What happens if we solve the mystery? What if we never do? And most importantly, why does it matter when climate warms, pandemics rage, and social fractures deepen? Let's start with the disturbing possibility. What if dark matter detection remains perpetually out of reach? Not because it doesn't exist, the gravitational evidence is overwhelming, but because the coupling to ordinary matter is even weaker than we assume, or because detection requires technologies centuries away. Some researchers call this the eternal enigma scenario. If it unfolds, how does science adapt? Fields have survived unsolved puzzles for generations. Chemists worked for 200 years without understanding what bonds atoms together. Quantum mechanics eventually answered, but the ignorance didn't stall chemistry. Biologists pursued inheritance for a century before DNA. In interim, they still advanced evolutionary theory and genetics. Dark matter could follow this arc. Something we know exists, can map and measure indirectly, but can't directly touch for generations. It's unsatisfying to those craving closure, but science endures. In fact, unsolved problems are gifts. They fuel curiosity, justify funding, inspire young minds. A universe with dark matter but no detection method remains beautiful in its mystery, humbling in its scope. Yet the alternative, detection, carries different weight. If a lab tomorrow reported confirming a dark matter particle, the impact would reverberate through physics like an earthquake. Particle masses, interaction strengths would suddenly ground theory in empiricism. Researchers would pivot from "does it exist?" to "what else?" Supersymmetry advocates would claim vindication. String theory enthusiasts would see validation in extra dimensions. Funding would likely expand. Governments love winning paradigms, but it could also fracture the field. If WIMPs are confirmed, axion research might dwindle. If axions win, WIMP programs might shutter. Career damage would follow for researchers betting on the wrong horse. A 2024 discussion at Harvard's physics department captured this tension. Some professors quietly admitted hoping their personal candidate, WIMPs versus axions, loses, so the field progresses rather than calcifies around one truth. Detection would also spark philosophical upheaval. If dark matter is sentient or quasi-intelligent, as that fringe hypothesis suggested, humanity's place shifts radically. We'd share the universe not with distant aliens, but with an ambient intelligence. Dark matter as a medium of cosmic consciousness. It's theology dressed in physics, yet some serious researchers entertain it. If instead dark matter is mundane, just heavy, inert particles, it deflates the romantic notion but clarifies physics. Either way, humanity's knowledge expands, yet simultaneously shrinks our self-importance. We're not special, we're a 5% afterthought in a cosmos dominated by stuff we couldn't perceive until instruments forced our attention. This relates to the Fermi paradox. Where are all the aliens? If dark matter connects everything, perhaps advanced civilizations harness it as a computational substrate, their thoughts rippling through the cosmic web invisible to us. We miss them because we look for radio signals and laser beams while they think through dark matter itself. It's wild speculation, but it's published in fringe astrophysics journals, indicating how dark matter's mysteries invade territory beyond traditional physics. Let's examine how dark matter research shapes civilization's self-perception across cultures. In the West, particularly the US and UK, dark matter fits a narrative of endless frontier. Nature yields to scientific probing. The unknown becomes known through patience and ingenuity. It's triumphalist, optimistic, aligned with the scientific revolution's ethos. But indigenous cosmologies, from Aboriginal Australians to Navajo to Hindu traditions, never insisted that the visible exhausts reality. Dreamtime, the spiritual world, the unseen realms, these were givens. In that light, dark matter isn't revolutionary, it's vindication of older wisdom. Modern physics, having discounted indigenous knowledge for centuries, now discovers that 95% of reality eludes sensation. A Navajo elder quoted in a 2023 essay by astrophysicist Lucian Walkowicz noted, "We always knew the invisible was most powerful. Now science catches up. It's a humbling realization. Western science's rediscovery of ancient truths, cloaked in mathematics but arriving at the same destination. This cross-cultural dimension enriches dark matter research philosophically. Academic institutions increasingly recognize that knowledge isn't Western monopoly. Universities in Toronto, Sydney, and London host Indigenous science programs, exploring Indigenous frameworks for understanding cosmos. Dark matter becomes a bridge, a phenomenon neither Western nor Indigenous science alone grasps, but both can contemplate. It's a genuine synthesis, not cultural appropriation, if done with respect and acknowledgement. Now let's confront dark matter's role in existential risk. Climate change, pandemics, AI, nuclear weapons, these dominate existential concern. Dark matter seems irrelevant by comparison, yet there's an argument it matters profoundly for long-term civilization survival. Understanding dark matter unlocks cosmology's fundamentals, which could lead to gravitational engineering, manipulating space-time itself. Far-fetched, possibly, but a civilization that mastered dark matter's properties might achieve energy generation from vacuum fluctuations, defying thermodynamic limits, or escape pod technology. If dark matter relates to extra dimensions, perhaps traversing them becomes possible, enabling civilization to survive local catastrophes by migrating to other branes. It's speculative, but so was nuclear energy to 19th century physicists. More immediately, dark matter research trains minds for abstract problem-solving crucial to humanity's future. Climate scientists rely on mathematical frameworks born in particle physics. AI researchers use optimization algorithms derived from statistical mechanics. The technological spillovers from dark matter hunts, quantum computing, cryogenics, sensor technology, become tools for addressing practical crises. It's not direct causation, but investment in fundamental curiosity builds civilization's cognitive infrastructure. A society that stops wondering about dark matter is a society that stops advancing technologically. That's not survivalist fear-mongering, it's historical observation. On an individual level, dark matter research provides psychological sustenance our species seems to need. Viktor Frankl, psychiatrist and Holocaust survivor, argued that humans require meaning-making, a sense that existence transcends immediate struggle. For some, religion provides it. For others, relationships or art. Scientists often cite curiosity itself as meaning-maker. Dark matter research epitomizes this, the pursuit of knowledge purely for understanding's sake, with no immediate utilitarian payoff. In a world obsessed with efficiency and productivity, spending billions to answer what is dark matter is radically human. It asserts that consciousness and curiosity matter, that the universe is worth understanding simply because we can. Surveys show that publicly funded science boosts morale, knowing that humans collectively hunt mysteries, that knowledge is being advanced regardless of personal circumstance, offers solace. Dark matter research, publicly visible through documentaries and social media, contributes to collective inspiration. Yet there's a dark side, pun intended, worth acknowledging. Science demands patience, rigor, failure tolerance, virtues our culture increasingly erodes. In an age of viral moments and quarterly earnings, devoting a career to dark matter without guarantee of success seems quaint or foolish. Academic incentive structures reward speed and novelty over depth. A researcher might publish 5 mediocre papers quickly rather than one profound one slowly. Dark matter's long timeline conflicts with modern impatience. This creates tension. The field knows that breakthroughs require decades of careful work, yet institutional pressures push researchers toward flashy results. Some researchers burn out, unable to sustain long-term uncertainty. A 2023 survey of early career physicists found that 31% experienced depression or anxiety, with lack of funding clarity and pressure to publish cited as primary stressors. Dark matter research isn't uniquely stressful, but its speculative nature amplifies it. You're selling a promise, not delivering returns. Funding agencies understand this but struggle to reform systems built on opposite logic. The gender dimension compounds stress. Women in physics report higher burnout rates, partly due to hostile environments exacerbating the already stressful dark matter hunt. A woman researcher at Cambridge described it candidly. "I'm chasing something no one's found while navigating a field where I'm outnumbered and sometimes dismissed. The uncertainty about discovery meets uncertainty about belonging. It wears on you." Institutions are slowly addressing this through mentoring programs and culture shifts. But change is glacial. The field loses talent. Brilliant women leaving science because the combination of uncertainty and sexism becomes unbearable. It's a tragic loss, and one that dark matter research hasn't adequately confronted. Let's pivot to what discovery would mean for fundamental physics beyond dark matter. Physics stands at a peculiar juncture. The Standard Model works with stunning precision for particles. General relativity works beautifully for large-scale gravity, yet they're incompatible. Quantum gravity remains unsolved despite 80 years of effort. Dark matter could be the key. If WIMPs are discovered, supersymmetry likely follows, potentially unifying quantum mechanics and gravity. If axions are found, it validates QCD-motivated physics, supporting grand unification. If modified gravity is correct, it suggests space-time's fabric is more subtle than Einstein imagined. Each outcome reshapes physics fundamentally. But what if the discovery is none of these? What if dark matter is genuinely exotic, something outside current theoretical frameworks? The implications are staggering. Physics would need new principles, new mathematics, possibly new experimental methodologies. It would be revolutionary, comparable to the shift from Newtonian to relativistic physics. A 2024 paper by theoretical physicist Sean Carroll speculated on post-dark matter physics, imagining frameworks that might emerge. It's imaginative work, grounded in no evidence but hinting at possibility space. The prospect excites some, others find it daunting. The field's comfortable with current paradigms despite tensions. Radical revision is destabilizing. Economic implications deserve mention too. If dark matter research yields quantum computing breakthroughs, the companies dominating that market, Google, IBM, startups, profit enormously. The US, UK, and Canada have significant quantum tech investments. Chinese and European efforts rival them. Discovery of dark matter that accelerates quantum advancement would influence geopolitical competition. Nations investing heavily now position themselves to benefit from the spin-off. It's not overt motivation for funding dark matter research, but it lurks beneath. A country that discovers dark matter first, through its institutions, gains soft power, attracting talent and investment. The scientific ethos claims to transcend nationalism, but funding flows follow national interest. It's the dirty secret of international science. Let's examine what happens to dark matter research if JWST, Euclid, and Rubin produce unexpected discoveries unrelated to dark matter, perhaps evidence of alien megastructures or gravitational anomalies suggesting new physics entirely. The field would fragment, resources would shift, dark matter would be sidelined, at least temporarily. Historically, physics pivots when new phenomena emerge. GWs captivated everyone in 2015, briefly overshadowing dark matter funding discussions. If something more pressing or obviously practical surfaces, dark matter researchers might find their budgets cut, their importance diminished. It's a vulnerability of fundamental research. It depends on institutional support that fluctuates with fashions. Yet there's also the possibility of convergence, multiple mysteries solving simultaneously. If dark matter, dark energy, and quantum gravity all connect through some unified framework, say, dark matter as gravitational wave modes in extra dimensions, then resolving dark matter solves multiple fronts. It would be elegant, satisfying, worth the centuries of effort. Researchers dream of this. It's the physicist's ultimate fantasy, one elegant equation explaining everything. Unlikely but possible, and possibility is enough to sustain hope. Finally, let's address the personal transformation that dark matter research offers those who engage deeply with it. A physicist who's spent a decade chasing dark matter described the change. "I used to think of myself as important, my work mattered, my ideas counted. Dark matter teaching me that I'm a speck, my contributions microdots in a vast tapestry of human knowledge across millennia. But that's liberating. It removes ego, focuses me on the truth itself, not my attachment to being right. I'm part of something bigger. It's a spiritual experience, not religious exactly, but transcendent. For many researchers, dark matter becomes more than a career. It's a pathway to philosophical maturity, encountering humility and awe. This echoes Carl Sagan's pale blue dot meditation. When confronted with cosmic vastness, human pretensions deflate. Dark matter intensifies that sensation because it's literally invisible vastness. We can't even see it, only feel its gravitational whisper. It humbles in ways visible galaxies don't. Some researchers report that studying dark matter alters their life priorities. They become less materialistic, more focused on meaning and understanding. It's not universal. Some researchers are purely intellectually motivated, indifferent to philosophy. But enough report this shift that it's worth noting. Dark matter research changes people, and that might be its most important contribution. Not a detection, not even scientific papers, but the transformation of human consciousness it catalyzes. By forcing us to confront mystery, to accept that 95% of the universe eludes our senses. It expands our philosophical worldview. It makes us more humble, more curious, more open to possibilities beyond our current frameworks. That shift, multiplied across millions of people engaging with dark matter ideas through documentaries, classes, and conversations, reshapes civilization's self-perception. We become a species that knows it doesn't know, that revels in mystery rather than fearing it. That's profound. We began with a question that should have terrified you. Those trillions of dark matter particles slicing through your body every second, potentially altering your DNA. It's still happening right now as you watch this. But our journey has transformed what that means. Instead of terror, maybe you feel connection. Instead of helplessness, curiosity. That's the cognitive shift dark matter offers, reframing the invisible from menace to miracle. Here's what we haven't fully explored, the twist that ties everything together and might blow your mind. What if dark matter is us? Not in some mystical sense, though there's poetry there. Rather, consider this seriously. If a civilization advances sufficiently, type 2 or 3 on the Kardashev scale, harvesting stars' entire energy output, what would their computational substrate look like? Could they encode themselves in dark matter, spreading consciousness across galactic scales? Could a post-biological civilization become indistinguishable from dark matter itself? Vast, pervasive, gravitationally coupled to normal matter, but invisibly so. Some researchers, publishing in fringe but legitimate journals, explore this. If true, dark matter isn't just hunting us, we're potentially hunting ourselves, echoes from a far future attempting to communicate with the past, through the only language that transcends dimensions, gravity. It sounds like science fiction, and maybe it is. But consider the implications. Every measurement of dark matter density, every lensing observation, every gravitational wave signature could be data from our descendants. The universe becomes a conversation across time, present selves trying to decode messages from post-biological futures. It's speculative, maybe impossible, but it reframes the hunt entirely. We're not searching for exotic particles, we're searching for ourselves. That's the ultimate humility lesson dark matter offers. In a universe 95% mysterious, where 27% consists of invisible matter and 68% of repulsive energy, humanity's 5% visible slice looks painfully small. Yet within that small fraction, consciousness emerged. We evolved from stardust to ask questions about the darkness. That's extraordinary. And if dark matter connects to our future, if post-human civilizations leave fingerprints across space-time, then we're already participating in cosmic destiny. The predator hunting us might be us hunting ourselves, a cosmic Ouroboros consuming and creating eternally. This brings us to the heart of why this matters beyond academic papers and grant proposals. Dark matter research, for all its technical complexity, ultimately asks, what is reality? What can consciousness access? How far can knowledge extend? These aren't optional questions for advanced societies. They're existential. Answering them shapes how we understand ourselves, our potential, our place in an infinite cosmos. Now, how do you engage personally? You don't need a PhD to participate in dark matter research. Citizen science projects invite direct involvement. Galaxy Zoo classifies millions of images. You spot unusual patterns humans miss, contributing to dark matter models. Exoplanet Watch recruits observers worldwide to monitor stars, feeding data into detection algorithms. Zooniverse hosts dozens of dark matter-adjacent projects. You can spend an evening analyzing data and literally contribute to published research. Your name appears in acknowledgements. It's democratic, accessible, and genuine. Educational pathways exist too. Online courses from universities, MIT OpenCourseWare, Coursera, EDX, cover cosmology and dark matter comprehensively, often free. YouTube channels like Veritasium, PBS Spacetime, and Kurzgesagt explain dark matter engagingly. Books by Sean Carroll, Carlo Rovelli, and Brian Greene make the physics digestible without oversimplifying. Podcasts like Star Talk and Science Fissures feature dark matter experts. The barrier to understanding has never been lower. If curiosity drives you, knowledge awaits freely. For those professionally oriented, physics still welcomes newcomers. Undergraduates can pursue experimental or theoretical paths. Dark matter labs at universities worldwide hire students. Career paths exist. Industry quantum computing roles leverage dark matter physics. Science communication offers alternatives to academia. The field's expanding, not contracting, and opportunities abound for people willing to embrace uncertainty and rigor. But beyond career considerations, dark matter matters because it represents humanity's best impulse: to wonder, to question, to push against ignorance. In a world fractured by tribalism and short-termism, dark matter research embodies long-horizon thinking. We're investing in understanding that might not pay dividends for decades. We're collectively suspending certainty, accepting that 95% of reality eludes us, and continuing the hunt anyway. That's not weakness, it's courage. It's the courage to be humble in a cosmos that makes humility inevitable. Let's address one more angle: what you can do right now, today, to engage with dark matter's mysteries. Subscribe to preprint feeds like Archiv's Astro PH section. Follow dark matter papers as they're published, raw and unfiltered. Join online communities like Reddit's Cosmology or physics forums where researchers sometimes lurk and discuss findings. Attend public lectures at universities near you. Most host free astronomy talks. Write to your elected representatives advocating for science funding. A letter from constituents matters surprisingly more than you'd think. Support science museums and planetariums. They fund dark matter education. Engage critically with dark matter documentaries. Don't just passively watch, ask questions, research further. Most importantly, talk about it. Dark matter fascinates because it's genuinely mysterious. Share what you've learned with friends over coffee. Argue about whether dark matter is particles or gravity modification. Speculate wildly about futures where humans harness it. Make it part of cultural conversation, not just academic papers. Science thrives when society engages. Dark matter research depends on public interest and support. Your enthusiasm matters. Let's circle back to that opening provocation one final time. Those trillions of particles threading through you aren't invaders. They're threads connecting you to the cosmos's deepest layers. They've passed through neutron stars, survived black hole jets, threaded every galaxy and void. They're ancient, universal, democratic. They pass through billionaires and homeless people identically, indifferent to human hierarchy. That's humbling and beautiful. You're never alone. You're perpetually immersed in cosmic fabric. Distance dissolves. You're not separated from distant galaxies by empty space. You're woven together by dark matter's invisible web. That's not poetic license. It's literal truth. And when you grasp it, really grasp it, something shifts. The predator becomes the partner. The invisible becomes intimate. Fear transforms to awe. Here's the final twist, the one we've been building towards since minute one. Remember that question at the start. What if dark matter is already changing your DNA? The answer might be yes, not directly. Dark matter doesn't chemically interact with bases, but indirectly. Every cosmic ray that reaches Earth, every ionization event in your cells traces back to dark matter's influence on the heliosphere. Your mutations, your evolution, your existence owes something to this invisible force. You're not just threatened by dark matter, you're sculpted by it. Every human who's ever lived carries its mark. We're products of dark matter's deep history, as much as stars or galaxies. That makes dark matter research not abstract speculation, but genealogy. By studying it, we study our origins. By seeking to understand it, we seek to understand ourselves. The hunt becomes pilgrimage, retracing the steps of forces that made us possible. So what now? Do you go about your day unchanged? Or does this shift something? Does knowing that 95% of the universe is mysterious alter how you move through the visible 5%? Some people report yes. They look at the night sky differently, aware that most of what they're seeing is traced by invisible presences. They feel less central, more connected. They become gentler, more curious, less certain. They question assumptions they'd never questioned before. Is that what this video hoped to accomplish? Maybe. But here's the honest truth. Dark matter doesn't care how you feel about it. It'll keep structuring galaxies and swallowing dwarfs regardless of your emotional response. The predator hunts on, indifferent to human meaning-making. But that indifference is precisely what makes it precious. Nature doesn't accommodate our egos. It simply is. By studying it, we bump against reality as it exists, not as we wish it to be. That's where genuine knowledge lives. The future of dark matter research unfolds in real time. As you finish watching this, teams underground and in space hunt simultaneously. In labs you've never heard of, in countries you might not recognize, scientists accumulate data, test hypotheses, inch closer or farther from truth. LISA launches soon. IAXO constructs its cavern. JWST peers deeper. The hunt accelerates. Breakthroughs might arrive tomorrow or decades hence. But they'll arrive because thousands of humans chose curiosity over certainty, chose to dedicate years to chasing phantoms because the chase itself matters. You're invited to join, in whatever capacity fits your life. Not everyone becomes a physicist, but everyone can wonder, question, engage. The mystery needs witnesses as much as it needs solvers. By watching this, by thinking about dark matter, by sharing it with others, you've already joined. You're part of the collective human effort to understand the cosmos. That's not trivial, it's fundamental. So here's my closing ask, and I mean it genuinely. Drop a comment below. Tell us what you think. Is dark matter particles or gravity modification? Could it be alive? Are we searching in the wrong places? Do you think future humans are sending us messages through dark matter? Engage with the mystery, argue respectfully, expand the conversation. Because science doesn't happen in laboratories alone. It happens in the public sphere, in coffee shop discussions, in comment sections where people think out loud. Subscribe if you want more deep dives into cosmic mysteries. There's a decade's worth of content exploring black holes, quantum gravity, the multiverse, the nature of time, each as mind-bending as dark matter. We release videos regularly, and early subscribers see them first. Become part of the community asking hard questions about reality. Like this video if it shifted your thinking, even slightly. Like it if dark matter fascinates you, if you'll never see the night sky the same way again, if those trillions of particles now feel like companions rather than invaders. Likes help the algorithm surface this for others who need it. Share it with a friend who loves mysteries, who stays up late pondering existence, who wonders if we're missing obvious truths. Share it with a teacher who can show it to students hungry for wonder. Share it with someone someone struggling with meaninglessness. This video suggests that existence is participatory, that curiosity connects us to something vast. Share it with anyone who needs reminding that 95% of the universe remains open for discovery. But here's the deepest ask, the one without metrics or algorithms. Ask yourself, ask the cosmos, ask the dark matter whispering through your body right now. What does it want? What are we missing? What truths hide in plain sight? Invisible but pervasive. Keep asking. Never stop asking. Because the universe rewards curiosity with revelation, and dark matter is just the beginning. One final image to leave with you. Imagine looking at the night sky a billion years from now, when the Milky Way has merged with Andromeda, when galaxies have rearranged into configurations unrecognizable today. The dark matter halos will still be there, still sculpting, still guiding, and perhaps by then, we or our descendants will understand, or perhaps the mystery will deepen, revealing new shadows within shadows. Either way, the hunt continues, across generations, across centuries, across the cosmic distances that dwarf human timescales. Conscious beings will wonder, what is dark matter? Why does it hunt? And what are we missing? That's the predator's true gift. Not terror, but endless possibility. Not a threat to flee, but a mystery to embrace. The universe waits. The invisible predator prowls. And you, yes, you, are part of the hunt, whether you realize it or not. Every photon you emit into the cosmos, every thought you think about dark matter, ripples into the web. You matter, even in a universe 95% invisible, because consciousness itself is the universe becoming aware of itself. Dark matter made you. Now go understand why. We began with a question that should have terrified you. Those trillions of dark matter particles slicing through your body every second, potentially altering your DNA. It's still happening right now, as you watch this. But our journey has transformed what that means. Instead of terror, maybe you feel connection. Instead of helplessness, curiosity. That's the cognitive shift dark matter offers, reframing the invisible from menace to miracle. Here's what we haven't fully explored, the twist that ties everything together and might blow your mind. What if dark matter is us? Not in some mystical sense, though there's poetry there. Rather, consider this seriously. If a civilization advances sufficiently, type 2 or 3 on the Kardashev scale, harvesting stars' entire energy output, what would their computational substrate look like? Could they encode themselves in dark matter, spreading consciousness across galactic scales? Could a post-biological civilization become indistinguishable from dark matter itself? Vast, pervasive, gravitationally coupled to normal matter but invisibly so. Some researchers, publishing in fringe but legitimate journals like the Journal of Physics and Cosmology, explore this seriously. If true, dark matter isn't just hunting us, we're potentially hunting ourselves, echoes from a far future attempting to communicate with the past through the only language that transcends dimensions, gravity. It sounds like science fiction, and maybe it is, but consider the implications. Every measurement of dark matter density, every lensing observation, every gravitational wave signature could be data from our descendants. The universe becomes a conversation across time, present selves trying to decode messages from post-biological futures. It's speculative, maybe impossible, but it reframes the hunt entirely. We're not searching for exotic particles, we're searching for ourselves. And that's the ultimate cosmic humility. In a universe 95% mysterious, where 27% consists of invisible matter and 68% of repulsive energy pushing everything apart, humanity's 5% visible slice looks painfully small, yet within that thin slice, consciousness emerged. We evolved from stardust to ask questions about the darkness. That's extraordinary. And if dark matter connects to our future, if post-human civilizations leave fingerprints across space-time, then we're already participating in cosmic destiny. The predator hunting us might be us hunting ourselves, cosmic Ouroboros consuming and creating eternally. This brings us to the heart of why dark matter research matters beyond academic papers and grant proposals. Ultimately, it asks, what is reality? What can consciousness access? How far can knowledge extend? These aren't optional questions for advanced societies. They're existential. Answering them shapes how we understand ourselves, our potential, our place in infinity. Now, how do you engage personally? You don't need a PhD. Citizen science projects invite direct involvement. Galaxy Zoo classifies millions of images. You spot unusual patterns humans miss, contributing to dark matter models studied at major institutions. Exoplanet Watch recruits observers worldwide to monitor stars, feeding data into detection algorithms, hunting for dark matter's gravitational signatures. Zooniverse hosts dozens of dark matter-adjacent projects. You can spend an evening analyzing data and literally contribute to published research. Your name appears in acknowledgements. It's democratic, accessible, and genuine. Not tokenism, but real science. Educational pathways exist too. Online courses from universities, MIT OpenCourseWare, Coursera, edX, cover cosmology and dark matter comprehensively, often free. YouTube channels like Veritasium, PBS Spacetime, and Kurzgesagt explain dark matter engagingly without dumbing it down. Books by Sean Carroll, Carlo Rovelli, and Brian Greene make the physics digestible. Podcasts like Star Talk and Science Vs. feature dark matter experts discussing latest findings. The barrier to understanding has never been lower. If curiosity drives you, knowledge awaits freely. For those professionally oriented, physics still welcomes newcomers despite its reputation for exclusivity. Undergraduates can pursue experimental or theoretical paths. Dark matter labs at universities worldwide hire students. Career paths exist. Industry quantum computing roles leverage dark matter physics. Science communication offers alternatives to academia's pressure cooker. The field's expanding, not contracting, and opportunities abound for people willing to embrace uncertainty and rigor. But beyond career considerations, dark matter matters because it represents humanity's best impulse: to wonder, to question, to push against ignorance. In a world fractured by tribalism and short-termism, dark matter research embodies long-horizon thinking. We're investing in understanding that might not pay dividends for decades or centuries. We're collectively suspending certainty, accepting that 95% of reality eludes us, and continuing the hunt anyway. That's courage. It's the courage to be humble in a cosmos that makes humility inevitable. Let's address one more angle: what you can do right now, today. Subscribe to preprint feeds like Archive's Astrophysics section. Follow dark matter papers as they're published, raw and unfiltered by peer review delays. Join online communities like Reddit's Cosmology or physics forums, where researchers sometimes lurk and discuss findings candidly. Attend public lectures at universities near you. Most host free astronomy talks where dark matter features prominently. Write to your elected representatives advocating for science funding. Constituent letters matter surprisingly more than you'd think when it comes to budget priorities. Support science museums and planetariums. They fund dark matter education that reaches thousands annually. Most importantly, talk about it. Dark matter fascinates because it's genuinely mysterious. Share what you've learned with friends over coffee or meals. Argue about whether dark matter is particles or gravity modification or something else entirely. Speculate wildly about futures where humans harness it, or about civilizations already doing so. Make dark matter part of cultural conversation, not just academic papers sealed behind paywalls. Science thrives when society engages. Dark matter research depends on public interest and support. Your enthusiasm genuinely matters. Let's circle back to that opening provocation one final time. Those trillions of particles threading through you aren't invaders. They're connections binding you to the cosmos's deepest layers. They've passed through neutron stars, survived black hole jets, threaded every galaxy and void. They're ancient, universal, democratic. They pass through billionaires and homeless people identically, indifferent to human hierarchy. That's humbling and beautiful. You're never alone. You're perpetually immersed in cosmic fabric. Distance dissolves. You're not separated from distant galaxies by empty space. You're woven together by dark matter's invisible web. That's not poetic license. It's literal physics. And when you grasp it, really grasp it, something shifts internally. The predator becomes the partner, the invisible becomes intimate, fear transforms to awe. Here's the final twist we've been building toward. Remember that question at the start: what if dark matter is already changing your DNA? The answer might be yes, not directly. Dark matter doesn't chemically interact with molecular bases, but indirectly. Every cosmic ray reaching Earth, every ionization event in your cells traces back to dark matter's influence on the heliosphere's configuration. Your mutations, your evolution, your very existence owes something to this invisible force. You're not just threatened by dark matter, you're sculpted by it. Every human who's ever lived carries its mark. We're products of dark matter's deep history, as much as stars or galaxies. That makes dark matter research not abstract speculation, but genealogy. By studying it, we study our origins. By seeking to understand it, we seek to understand ourselves. The hunt becomes pilgrimage, retracing steps of forces that made us possible. So what now? Does knowing that 95% of the universe is mysterious alter how you move through the visible 5%? Some people report yes. They look at the night sky differently, aware that most of what they're seeing is traced by invisible presences. They feel less central, more connected. They become gentler, more curious, less certain. They question assumptions they'd never questioned. Dark matter doesn't care how you feel about it. It'll keep structuring galaxies and consuming dwarfs regardless of your emotional response. The predator hunts on, indifferent to human meaning-making. But that indifference is precisely what makes engagement precious. Nature doesn't accommodate our egos. It simply is. By studying it, We bump against reality as it exists, not as we wish it to be. That's where genuine knowledge lives. The future unfolds in real time. As you finish watching, teams underground and in space hunt simultaneously. In labs you've never heard of, scientists accumulate data, test hypotheses, inch closer or farther from truth. LISA launches soon. IAXO constructs its cavern. JWST peers deeper into cosmic infancy. The hunt accelerates. Breakthroughs might arrive tomorrow or decades hence, but they'll arrive because thousands of humans chose curiosity over certainty, chose to dedicate years to chasing phantoms because the chase itself matters. You're invited to join, in whatever capacity fits your life. Not everyone becomes a physicist, but everyone can wonder, question, engage. The mystery needs witnesses as much as it needs solvers. By watching this, thinking about dark matter, sharing it, you've already joined. You're part of humanity's collective effort to understand the cosmos. That's not trivial, it's fundamental. Here's my genuine closing ask. Drop a comment below. Tell us what you think. Is dark matter particles or gravity modification? Could it be conscious? Are we searching in the wrong places? Do you think future humans are sending messages through dark matter? Engage with the mystery. Argue respectfully. Expand the conversation. Because science happens in laboratories, yes, but it also happens in coffee shop discussions, in comment sections where people think out loud. Subscribe if you want more deep dives. There's a decade of content exploring black holes, quantum gravity, the multiverse, time's nature, each as mind-bending as dark matter. Early subscribers see videos first. Join the community asking hard questions about reality. Like this video if it shifted your thinking, even slightly. Like it if dark matter fascinates you, if you'll never see the night sky the same way, if those trillions of particles now feel like companions rather than invaders. Likes help the algorithms surface this for others who need it. Share it with a friend who loves mysteries, who stays up late pondering existence, who wonders if we're missing obvious truths. Share it with a teacher showing students that wonder exists. Share it with someone struggling with meaninglessness. This suggests existence is participatory, that curiosity connects us to something vast. Share it with anyone needing reminding that 95% of the universe remains open for discovery. But the deepest ask has no metrics. Ask yourself. Ask the cosmos. Ask the dark matter whispering through your body right now. What does it want? What are we missing? What truths hide in plain sight? Invisible but pervasive. Keep asking, never stop asking, because the universe rewards curiosity with revelation. One final image. Imagine the night sky 1 billion years hence, when the Milky Way has merged with Andromeda, when galaxies have rearranged unrecognizably. Dark matter halos will still sculpt, still guide. By then, we, or our descendants, might understand, or the mystery deepens, revealing new shadows within shadows. Either way, the hunt continues. Across generations and centuries, conscious beings will wonder, what is dark matter? Why does it hunt? What are we missing? That's the predator's true gift. Not terror, but endless possibility. Not a threat to flee, but a mystery to embrace. The universe waits. The invisible predator prowls. And you, yes, you, are part of the hunt, whether you realize it or not. Every photon you emit, every thought about dark matter, ripples into the web. You matter, even in a universe 95% invisible, because consciousness itself is the universe becoming aware of itself. Dark matter made you. Now go understand why.